Inside Volkswagen's massive production plants, every car is built with clockwork precision and decades of German engineering experience. From robotic welding lines to intricate final inspections, the entire process is a blend of speed, accuracy, and innovation. In this video, we'll take you inside the factory to see exactly how a Volkswagen goes from raw materials to the open road. The creation of a Volkswagen Golf, one of the most iconic hatchbacks in automotive history, begins long before any metal is stamped or bolts are torqued. To truly appreciate the intricacy and precision of its manufacturing, we need to understand that this process represents the culmination of decades of engineering refinement, logistical coordination, and factory automation. It is not merely the assembly of components, but the orchestration of thousands of interdependent systems working in harmony, each with a dedicated role in transforming raw materials into a vehicle ready to roll off the line and onto the world's roads. The process begins at the heart of the operation, the Volkswagen manufacturing plant. One of the most famous Golf production facilities is located in Wolfsburg, Germany, where massive halls the size of several football fields stretch out in every direction. The atmosphere inside is clinical, controlled, and buzzing with quiet energy. Contrary to what one might expect, these spaces are not chaotic or deafening. They are meticulously organized, highly automated environments where human expertise collaborates with robotic precision to produce each vehicle to exacting standards. The first chapter in the physical birth of a Golf begins with the fabrication of the car's body shell. This process is commonly referred to as body in white, and it involves the welding and joining of raw sheet metal components that form the structural skeleton of the vehicle. These metal sheets typically arrive at the factory in pre-cut and coiled form, having been sourced from steel and aluminum suppliers who produce automotive-grade alloys with specific mechanical properties such as tensile strength, corrosion resistance, and energy absorption. Volkswagen has stringent quality controls on these materials, inspecting incoming shipments with laser scanners, chemical analysis equipment, and tensile testing machines to ensure that every roll meets the necessary specifications for forming and crash safety. Once approved, the metal sheets are uncoiled and fed into gigantic press machines, many stories tall, in what is known as the stamping area. These presses are a marvel in themselves, each capable of exerting thousands of tons of pressure. Using a combination of progressive and transfer dies, massive steel molds engineered to exact tolerances, these machines punch, bend, and form individual components like doors, hoods, roofs, floor panels, and side frames. Each die can weigh up to 40 tons and requires highly precise installation. The press line operates with the rhythmic certainty of a mechanical heartbeat, with each panel ejected onto a conveyor system that ferries it toward the next phase of production. From here, the stamped panels enter the body shop. This area is perhaps the most robot-dominated zone of the entire plant. Hundreds of robotic arms, painted in Volkswagen's signature orange or yellow, perform an intricately choreographed ballet of spot welding, laser welding, and riveting. These robots are guided by 3D coordinate programming and vision systems that allow them to make microscopic adjustments in real time. Their work is critical, as the dimensional accuracy of the welded body frame dictates how well later components, like the drivetrain and interior modules, will fit. The vehicle begins to take shape as floor panels are married with the side structures. Roofs are laser welded into place, and reinforcement beams are added to strengthen key impact zones. The welding robots are just one part of this highly automated process. In certain sections, human operators are still essential, particularly for tasks requiring dexterity, visual inspection, or adaptation to model variants. At these stations, workers equipped with pneumatic tools and ergonomic lifts work alongside the robots to install structural reinforcements, apply bonding agents, or verify alignment with laser-calibrated measurement systems. Every completed body shell is then run through a geometric measurement tunnel, where a series of cameras and lasers scan the surface down to the sub-millimeter level, ensuring that each vehicle conforms precisely to Volkswagen's quality blueprint. Once the body-in-white structure is completed and quality verified, the next transformative phase begins, the painting process. But before any color is applied, the raw metal body must be prepared to resist corrosion and adhere properly to the paint layers. The shell first passes through a cleaning and pre-treatment bath, typically involving a series of immersion tanks where it is cleaned of oils, particulates, and oxidation. This is followed by a process known as cathodic electrocoating, or e-coating. Here, the entire body is submerged in an electrically charged bath containing anti-corrosion primer particles. A low voltage current causes the primer to be drawn onto every metal surface, even inside closed box sections, providing complete and uniform protection. After e-coating, the body is dried in a curing oven and then transferred into the paint booths. These clean rooms are maintained at highly controlled temperature, humidity, and dust levels. The next steps involve the application of a primer layer, base coat, and clear coat, each sprayed using high-precision rotary atomizers. Robots again take the lead here, moving with fluid, sweeping motions to ensure a uniform paint film. Each coat is flash-dried between applications, and the final clear coat is cured in another high-temperature oven. Color accuracy and surface quality are assessed by specially trained technicians, often under special light tunnels that reveal even the most subtle defects or inconsistencies in the paint finish. With the painted body now cooled and cured, it proceeds to the marriage with the mechanical underpinnings, the powertrain, suspension, and chassis components. This phase marks the beginning of the general assembly process, which is one of the most logistically complex and human-involved areas of the plant. The painted body is mounted onto a continuously moving conveyor line known as the assembly line or production line, and begins its journey through a sequence of stations, each responsible for a specific set of tasks. One of the first major milestones on this line is the marriage station. Here, the body shell is carefully lowered onto a pre-assembled chassis, which includes the engine, transmission, front and rear axles, brake lines, fuel system, and other underbody modules. This process is performed using automated lifting gantries equipped with positioning sensors and torque control systems, ensuring that every bolt, mount, and fastener is attached with the correct torque specification. At this stage, precision is paramount. The alignment of engine mounts, suspension geometry, and drivetrain clearances are all verified using computer-aided fixtures and sensor feedback systems. As the car progresses down the line, workers and robots alternate in adding increasingly complex subsystems. Wiring harnesses, which have been pre-assembled in a separate part of the plant, are routed through the vehicle's interior and connected to key modules. These harnesses are essentially the vehicle's nervous system, containing hundreds of electrical wires that link sensors, control units, lighting, safety systems, and infotainment components. Routing these bundles accurately and securing them with clips, grommets, and tie wraps is both an art and a science, requiring a balance between accessibility, safety, and electromagnetic shielding. Following this, the interior components begin to enter the scene. Dashboards, HVAC units, center consoles, and infotainment displays are installed using guided insertion tools and laser alignment rigs. The seats, which are often built in a just-in-time fashion by a nearby supplier, are delivered directly to the line and bolted in place using high-torque pneumatic tools. Throughout this process, every module is scanned with a barcode reader to ensure traceability. This level of digital tracking allows Volkswagen to log the exact batch, supplier, and assembly timestamp for every major component, creating a complete digital twin of the vehicle's production history. By this point, the Golf has become instantly recognizable, with its iconic silhouette now cloaked in paint and outfitted with much of its interior. However, many critical systems have yet to be tested or activated. That next phase, electrical testing, fluid filling, and calibration, marks a turning point in the assembly process, transitioning the Golf from a mechanical object to a functioning machine. As the Volkswagen Golf continues its progression down the general assembly line, it begins to cross into one of the most critical sections of production: system initialization and functional testing. This stage transforms the vehicle from a silent shell into an electrically alive machine. It is here that the electronic control units, or ECUs, are first brought online. These digital brains govern virtually every function in the vehicle, from fuel injection timing and anti-lock braking response to climate control algorithms and sensor-based driver assistance systems. The Golf contains dozens of these ECUs, each responsible for different subsystems, and all interconnected through a series of high-speed data buses such as CAN, L-Line, and FlexRay. Before any electrical current is sent through the system, technicians connect the vehicle to a centralized factory diagnostic interface via a port located under the dashboard. The same OBD port later used by service technicians and inspection facilities. Using specialized software, factory workers upload the correct firmware and configuration data into the ECUs. This process is not merely about flashing software. It's about synchronizing every system to the specific build of that vehicle. Variables like engine type, transmission variant, lighting package, regional compliance requirements, and customer-selected options all influence how the ECUs behave. This digital handshake ensures the car will operate correctly and meet both performance and regulatory expectations. Once the ECUs are initialized, the next step is electrical verification. Automated test rigs are used to check that every connection, sensor, and actuator is functioning correctly. These rigs apply voltage and resistance checks through the wiring harness, lighting systems, and control modules. Even minor faults, such as an improperly seated connector or excessive resistance in a wire, are immediately flagged by the system. Any detected issues cause the car to be diverted from the main line to a specialized diagnostic bay where trained technicians perform pinpoint troubleshooting and rework, ensuring that no electrical faults go undetected. Parallel to the electrical system bring-up, the vehicle also receives its initial fill of operational fluids. These include engine oil, coolant, brake fluid, transmission fluid, power steering fluid if hydraulic, and in some cases, refrigerant for the air conditioning system. The filling process is performed by robotic dispensing arms that are pre-programmed to deliver the precise volume and type of fluid required for each model. Flow meters, pressure sensors, and digital records ensure absolute consistency and prevent underfilling or contamination. The fuel tank is also filled with a small amount of test fuel, typically around 5 to 10 liters, sufficient for initial startup, emissions testing, and short-range driving tests later in the process. After fluid filling, one of the most dramatic moments in the assembly process occurs: the engine start. This is not done casually, nor is it done without extensive prior checks. Once all systems are confirmed ready, a technician activates the ignition via the factory diagnostic system or a standard key fob, causing the engine to turn over for the first time. Sensors throughout the vehicle immediately begin transmitting data: engine RPM, oil pressure, coolant temperature, voltage levels, and emission sensor feedback, all of which are monitored live by quality assurance software. If the engine does not start within a certain time window, or if any critical values fall outside the permissible range, the vehicle is automatically flagged for further inspection. Assuming a successful startup, the next phase involves dynamic system checks. These include actuating key mechanical subsystems to ensure proper functionality. The steering is rotated lock to lock to test assist levels and detect any binding. The brakes are pressurized to confirm pedal feel and hydraulic integrity. The transmission is cycled through its gears, with automatic models shifting through each range while stationary, and manual models undergoing clutch engagement tests. Additional functions like power windows, central locking, infotainment screens, headlight alignment, and mirror adjustments are also verified at this stage. All of these checks are conducted on the moving assembly line or at dedicated inspection stations known as end-of-line testers. These stations are equipped with rollers, sensors, cameras, and feedback terminals that allow technicians to observe live data streams. If a vehicle passes all of these checks, it is allowed to proceed to the next major step: wheel mounting and torque application. At this point, the Golf receives its wheels and tires, which have been assembled and balanced in a separate part of the plant. Tire suppliers often work in close partnership with the assembly plant, sometimes even maintaining satellite facilities on site to deliver tires in real time according to the production sequence. The wheels are mounted using robotic arms equipped with torque sensing screwdrivers. These tools are programmed with model-specific torque settings and follow a defined tightening sequence to ensure that every lug nut is fastened uniformly, reducing the risk of vibration or uneven stress on the brake rotors. After wheel installation, the vehicle is lowered off its assembly jigs and finally touches the ground under its own weight. This moment, often called first contact, marks the vehicle's readiness for dynamic testing. It is now fully assembled, fully functional, and ready to move under its own power. But production does not end here. The vehicle is then driven, slowly and under tight controls, to the next area of the plant: the rolling road test bench, also known as the dynamometer station. Here, the car is placed onto a set of rollers that simulate driving conditions while keeping the vehicle stationary. The purpose of this test is to perform a full-spectrum functional evaluation under load. The vehicle is accelerated, decelerated, and driven at varying speeds while sensors record engine performance, emissions output, braking effectiveness, and drivetrain behavior. Advanced vision systems check headlight aim and beam shape. Microphones measure cabin noise under acceleration. Even the wiper system is tested using artificial rainfall nozzles while the car is driven at simulated speeds. If any aspect of this test fails to meet Volkswagen's internal benchmarks, the car is again pulled from the line and sent to a rework zone. Here, highly trained specialists diagnose and resolve the issue, whether it be a misaligned sensor, a software glitch, or an out-of-spec component. Vehicles cannot proceed to final inspection until they achieve a perfect score on the dynamometer test. Following this dynamic validation, the car enters the final quality inspection area. This zone is brightly lit and staffed with quality control inspectors who perform a visual and tactile examination of every surface, seam, and feature. Paintwork is scrutinized under color-correct lighting to detect any blemishes, orange peel, or dust inclusions. Door gaps and panel alignment are measured with precision gauges. Interior materials are checked for fit, finish, and correct placement. Inspectors open every door, operate every switch, and sit in the car to check for rattles, uneven padding, or installation errors. This is often the first time someone interacts with the Golf as a complete product, and every detail matters. Once the vehicle passes its final inspection, a protective wrap is applied to its most vulnerable surfaces, typically the hood, roof, mirrors, and door edges, to prevent damage during transport. Barcodes and shipping labels are affixed, and the vehicle is driven to the logistics yard, where it joins a massive fleet of completed Golfs waiting for shipment. These yards are organized with incredible precision, with each car's location digitally tracked for efficient loading onto transport trucks or rail cars. While this marks the end of the physical assembly process within the factory walls, the story of each Golf is far from over. It now enters the distribution and logistics phase, a sprawling global network designed to deliver each vehicle to its final destination as quickly and safely as possible. But that segment of the journey involves a separate layer of logistical planning, international coordination, and dealership preparation, all of which merit a detailed explanation of their own. The freshly assembled Volkswagen Golf, now cloaked in its protective transport films and validated through layers of mechanical, electrical, and aesthetic inspections, begins its transition out of the factory environment and into the broader world. This stage, the post-production logistics and distribution process, is a sophisticated dance of real-time tracking, intermodal transportation, and region-specific compliance, all of which are critical to ensuring that each vehicle reaches the correct dealer in the correct configuration and in pristine condition. After final inspection, the Golf is driven from the assembly line to the Vehicle Logistics Center, often located adjacent to the main manufacturing facility. Here, trained drivers guide the vehicles along designated internal roads, maintaining low speeds and following strictly mapped routes to avoid cross-contamination or accidental damage. At the staging yard, vehicles are sorted based on destination markets, production variants, and transport mode. Some will head to domestic dealerships via truck, while others will be loaded onto trains for long-haul land journeys. For global markets, many Golfs are prepared for shipping by sea, making their way to port via specialized car-carrying rail networks. Before any Golf leaves the staging yard, a final scan is performed. Using handheld barcode scanners or RFID readers, workers verify the vehicle's unique VIN, vehicle identification number, against the factory's production records. This cross-referencing ensures that the car has passed all necessary quality gates, has been matched with the correct transportation order, and is headed to the appropriate regional hub. Additionally, certain destination countries require extra compliance steps before a vehicle can legally enter or be registered, such as emissions documentation, safety certification, or region-specific firmware updates to the vehicle's ECUs. These requirements are embedded into the logistics planning software, and vehicles are automatically routed to compliance zones where technicians apply the necessary updates or decals before departure. Once verified and queued, the Golf is prepared for loading onto a transport carrier. For truck transport, specialized vehicle haulers equipped with multi-level ramps are used. These carriers are engineered to accommodate various vehicle sizes while maximizing capacity and maintaining balance for road stability. Loading is conducted with extreme care. Each car is driven up ramps and secured using wheel straps, chocks, or integrated platform locks that prevent movement during transport. Drivers are trained not only in vehicle handling, but also in load balancing, ensuring that the distribution of weight across the trailer complies with legal road limits and mechanical tolerances. For long-distance rail transport, the Golf is moved onto enclosed or open-sided car transport wagons. These wagons can hold up to a dozen vehicles per unit and are designed to withstand the rigors of long-haul journeys across multiple climate zones. Rail is favoured for its cost efficiency and environmental impact, particularly for routes within Europe, where dense rail infrastructure allows cars to be delivered to regional distribution centres with minimal handling. Once the vehicles reach their destination hubs, often located just outside major cities, they are transferred to final mile delivery trucks that ferry them to individual dealerships. When the Golf is destined for international markets outside of Europe, such as North America, Asia, or Australia, it must be transported by sea. This requires loading the vehicles onto large roll-on/roll-off cargo vessels, also known as ro-ro ships. These enormous ships are essentially floating multi-story parking garages, capable of holding thousands of vehicles at once. At the port terminal, cars are driven aboard by logistics personnel who work under tight schedules to fill each ship efficiently. Vehicles are parked according to a precise digital manifest, which maps each car's location by deck, row, and position for accurate unloading at the destination port. Ro-ro shipping requires a high level of environmental control. Vessels are designed to maintain safe humidity levels, minimize exposure to salt air, and prevent the movement of cars in rough seas through a system of tie-down points and loading jacks. Once the vehicle arrives in its destination country, it goes through a process known as port processing. This includes customs clearance, regulatory inspections, and any market-specific modifications. Depending on the country, this might involve the installation of alternative language infotainment software, the addition of local safety equipment like fire extinguishers or first aid kits, or the application of region-specific emblems and badges. Vehicles are once again inspected for transport-related damage, cleaned, and detailed before being sent to the dealership. But while distribution is an essential part of the car's journey, it is merely the final chapter in the broader industrial narrative. To truly understand the full scope of how a Volkswagen Golf comes to be, we must look beyond the visible car to the invisible infrastructure that supports its manufacture, the supplier network, component fabrication, and just-in-time logistics that converge at the assembly plant, like veins feeding into a living heart. Every Golf is made up of more than 30,000 individual parts, many of which are produced not by Volkswagen directly, but by a web of Tier 1 and Tier 2 suppliers across the globe. These include suppliers specializing in electronics, seats, glass, tires, injection molded plastics, turbochargers, radiators, axles, and much more. These companies operate under strict quality and timing requirements, often working within a just-in-sequence framework. This means that not only must the parts arrive just in time to avoid stockpiling or shortages, but they must also arrive in the exact order in which they are needed on the line. To enable this, Volkswagen uses a combination of supplier parks, regional distribution centers, and digital planning tools that forecast production demand down to the minute. Many of these suppliers operate satellite facilities on or near the Volkswagen campus itself. These microfactories are tightly integrated into the main production loop. For instance, a seat supplier may receive a digital order moments after a car body is painted and matched to a particular trim level. Within hours, the seat is built, quality checked, and delivered to the assembly line just as the car arrives at the station where it will be installed. The just-in-time system dramatically increases efficiency and reduces warehousing costs, but it also demands precision and resilience. Any disruption in the supply chain, whether due to weather, labor issues, or global events, can ripple across the production schedule. To manage this complexity, Volkswagen employs advanced manufacturing execution systems and enterprise resource planning software that communicate with suppliers, forecast demand, and adjust schedules in real time. Each supplier must adhere to predefined quality protocols, including statistical process control, failure mode analysis, and traceability documentation, which are routinely audited by Volkswagen's internal teams. On the component level, many key parts are manufactured using highly specialized processes before they ever reach the main assembly line. Take, for example, the engine, the mechanical heart of the Golf. Engine blocks begin their life as raw aluminum or cast iron, melted and poured into precision molds using high-pressure casting methods. Once solidified and cooled, the blocks are machined using CNC equipment that drills, hones, and surfaces the bores and mating faces to tolerances often measured in microns. Crankshafts, camshafts, pistons, and cylinder heads undergo similar processes, each passing through multiple heat treatment, grinding, and quality inspection stages before final assembly. The completed engine is then mated with its transmission. Tested on a cold bench, a fixture that simulates operation without fuel or combustion, and sent to the main production hall. There, it joins the sequence of drivetrain assemblies that will eventually meet their respective body shells on the marriage line. Similarly, high-tech components like digital dashboards, ADAS sensors, and infotainment head units are built and tested in cleanroom environments to prevent contamination or electrostatic damage. These electronic assemblies are subjected to functional tests, environmental stress simulations, and firmware updates before being sent to the main line. At the plant level, all of these moving parts, mechanical, logistical, and digital, converge into what is often described as a cyber-physical production system. Assembly lines are increasingly governed by AI-enhanced predictive analytics, machine learning algorithms that forecast wear on machinery, and autonomous material handling vehicles that navigate factory floors using LiDAR and GPS. Real-time dashboards allow factory managers to monitor production flow, equipment uptime, part inventories, and worker ergonomics from centralized control centers. Robots, collaborative arms known as cobots, and human workers form a hybrid workforce that constantly adapts to changes in demand, variant complexity, or technological updates. All of this results in a manufacturing ecosystem that is as complex and finely tuned as the vehicles it produces. The Volkswagen Golf, which might appear to the average buyer as a simple compact hatchback, is in reality the output of a global network of suppliers, engineers, robots, and logisticians working in concert with millisecond-level precision. It is a product born of thousands of hands and millions of decisions, every one of them contributing to the moment when the car's engine starts for the first time, the headlights blink to life, and it begins its journey toward the showroom floor. As the story of the Volkswagen Golf continues within the factory walls, we now shift focus to the critical yet often overlooked phase that follows the assembly and functional testing of the physical vehicle. Final calibration, detailed software programming, and human-centered quality control measures that ensure not just mechanical soundness, but also driving experience fidelity, safety compliance, and brand consistency. This stage marks the final opportunity for engineers and technicians to refine the car's personality, the way it feels, sounds, and responds before it ever reaches a dealership. Once the vehicle passes its rolling road test, electrical verification, and cosmetic inspections, it enters what's referred to in modern manufacturing as the calibration and personalization loop. Here, technicians interface with the vehicle's multiple electronic control units, upwards of 50 in many Golf variants, to fine-tune parameters such as steering weight, throttle response, transmission shift points, air conditioning behavior, and even ambient lighting modes. Although these parameters are based on predefined model profiles, small adjustments are often needed to account for tolerances in component performance, environmental conditions, and the specific variant configuration of the vehicle. This process uses a digital toolchain, often referred to as a centralized vehicle configuration system. The technician connects a specialized programming console to the vehicle's onboard diagnostics port. Through this interface, the system retrieves the vehicle's build sheet, a digital summary of every major component, trim level, engine type, and region-specific setting installed during production. Based on this, the technician downloads the relevant firmware packages and configuration profiles from a secure Volkswagen server. These files include calibrations for dynamic systems like ESC, lane keeping assistance, adaptive cruise control, and the steering rack's servo control logic. The software installation itself is performed with high redundancy and validation steps. Each module receives a cryptographic checksum, ensuring the integrity of the code after download. The system then runs a diagnostic sweep, verifying that all ECUs are correctly communicating across the vehicle's CAN and LN bus architecture. Should any module fail to respond or report a checksum mismatch, the vehicle is flagged and removed from the main line for specialized reprogramming in a secure rework area. This level of rigor is necessary, not only to ensure reliability and drivability, but also because these software systems control functions directly linked to passenger safety. Following calibration, the vehicle passes through a sequence of human-led evaluations known internally as sensory audits. In a world increasingly governed by automated inspection and robotic precision, this human touch remains indispensable. Sensory audit teams, often composed of master technicians and experienced inspectors, evaluate things that machines cannot easily quantify. They listen for rattles or unexpected noises while operating various components, apply gentle force to test the feel of buttons and switches, and run their hands along upholstery seams to detect imperfections in fit or material finish. These teams test the firmness of seat padding, assess the resistance in climate control knobs, and verify the damping in the glove box lid's opening motion. This inspection process is not random. Each inspector follows a detailed checklist created for the Golf's specific variant, whether it's a base TSI model or a performance-oriented GTI. Every tactile point of interaction with the driver or passenger is scrutinized. The sound of the door closing, the feedback of the turn signal stalk, the clarity of the infotainment screen. Even the air vents are examined for smooth adjustability and structural integrity. These subtle, almost imperceptible qualities play a vital role in shaping customer perception. They influence whether a driver describes the Golf as solid, refined, or thoughtfully engineered. And Volkswagen knows that these sensory markers directly translate to brand loyalty. Parallel to the sensory audit is a final high-pressure water test. Here, the vehicle is driven into a sealed chamber where it is subjected to a simulated rainstorm, complete with directed nozzles spraying water at high pressure from multiple angles. The goal is to identify leaks around door seals, windshield bonds, taillights, and underbody grommets. As the water jets barrage the vehicle, sensors inside the cabin monitor for moisture ingress, while technicians inspect areas with flashlights and absorbent strips to detect even minute amounts of seepage. Any vehicle that fails this test is returned to a specialized sealing and bonding repair zone where issues are addressed before retesting. Once these final inspections are complete, the vehicle is officially released from production. However, in a modern Volkswagen plant, this release is also the beginning of a data-rich archival process. A complete digital profile of the vehicle, from every torque specification logged during assembly, to the paint batch number, to the firmware version of the braking system, is uploaded to a central database. This digital twin acts as a permanent reference for the vehicle throughout its service life. If a recall or service bulletin is ever issued in the future, this record allows Volkswagen to identify not only which vehicles are affected, but precisely what components or subsystems were installed and when. It is also worth noting that many Golf variants are produced with advanced driver assistance systems, which require a final calibration procedure using sophisticated optical targeting tools. This is especially critical for features like lane keeping assistance, traffic sign recognition, autonomous emergency braking, and adaptive cruise control, which rely on a front-facing camera, radar sensors, and sometimes LiDAR. These sensors must be calibrated in relation to the car's central axis, suspension height, and tire circumference. The calibration process is performed in a controlled bay using visual markers, checkerboard targets, and reference panels, positioned at known distances. Specialized software then guides the technician through alignment adjustments and performs a verification routine, simulating input data to test the system's reactions. The factory also considers the growing importance of software updates throughout a vehicle's lifecycle. Increasingly, Golf models are being built with over-the-air update capabilities. This means that certain vehicle functions can be improved or corrected remotely without visiting a dealership. To enable this, each vehicle must be registered with Volkswagen's secure update server and fitted with a telematics control unit capable of handling encrypted data downloads. Before leaving the plant, the vehicle undergoes a brief connectivity test using a private cellular or Wi-Fi network. This ensures that the vehicle can receive updates in the field and that the security keys assigned during factory programming are valid and authenticated. Another major focus of final stage production, particularly in recent years, is environmental sustainability. Volkswagen has implemented comprehensive measures to reduce the ecological footprint of Golf manufacturing. For example, paint shops, traditionally among the most energy-intensive and pollutant-heavy parts of vehicle production, now use water-based paints and advanced overspray capture systems to reduce volatile organic compound emissions. Waste heat from ovens and drying tunnels is recovered and recycled into the factory's climate system. Water used in the electrocoating and wash booths is treated on-site and reused in a closed-loop system. Powering the factory itself is a growing area of environmental emphasis. Many of the plants where the Golf is manufactured have transitioned to renewable energy sources, such as wind or hydroelectric power. In Wolfsburg, for instance, Volkswagen has partnered with regional utilities to supply the production lines with green electricity. Additionally, automated lighting, motion sensors, and energy-efficient drive systems on robots and conveyors contribute to reduced overall consumption. These investments not only lower the per-vehicle carbon output, but also align with Volkswagen Group's broader Way to Zero strategy, a commitment to climate-neutral mobility and carbon-neutral production by 2050. Within the plant, materials management is handled with sustainability in mind as well. Steel and aluminum scrap generated during stamping operations are carefully sorted, compressed, and sent to recycling centers, some of which are reintegrated back into the supply chain. Plastics from production offcuts or rejected trim parts are ground down and reused in non-visible components. Even packaging materials used to deliver parts, such as crates, dividers, and protective films, are tracked and returned to suppliers in a closed-loop logistics model. What makes the Volkswagen Golf's production so remarkable is not just the car itself, but the systems, philosophies, and technological ecosystems that produce it. Each vehicle embodies the cumulative effort of thousands of hours of engineering, years of supplier relationships, terabytes of design simulations, and millions of precisely orchestrated manufacturing movements. What rolls off the line is not a standalone product, but the physical representation of a global, highly optimized industrial organism. One designed to balance quality, efficiency, innovation, and sustainability in every nut, panel, circuit, and drop of fuel or electricity it consumes. As we move deeper into the Volkswagen Golf's manufacturing story, we begin to explore the systems behind the systems, the cutting-edge technologies and organizational strategies that elevate Golf production beyond traditional automotive assembly. Much of this innovation centers around Volkswagen's use of modular platforms, intelligent factory automation, and advanced data analytics, all of which have transformed not just how a Golf is made, but how efficiently, flexibly, and sustainably it can be produced, alongside a range of other vehicle models. At the core of this evolution is Volkswagen's MQB platform, short for Modulare Kurbaukasten, which translates to Modular Transverse Matrix. Introduced in the early 2010s, this platform underpins not only the Golf, but also a wide range of vehicles across Volkswagen Group's brands, including the Audi A3, Seat Leon, and Skoda Octavia. The brilliance of the MQB platform lies in its standardized architecture. Critical hard points, such as the position of the engine, the distance between pedals and front axle, and mounting locations for crash structures are fixed across models, while allowing flexible variation in wheelbase, track width, and body style. This enables massive economies of scale and allows the Wolfsburg plant, among others, to produce multiple models on a single line with minimal retooling. In practice, this means that a Golf might be built on the same line as a Tiguan or a Touran, using many of the same robotic stations, fastening tools, and software configurations. Tooling carts, parts bins, and robotic arms are designed with adaptability in mind. Instead of having separate jigs for each model, multifunctional fixtures and programmable robots detect the incoming body type via RFID tags or QR codes and adjust themselves in real time. A welding robot, for example, might apply different sequences or torque levels, depending on whether it is working on a Golf hatchback or a longer wheelbase estate model, all without human intervention. This production flexibility is supported by a sophisticated manufacturing execution system, a digital nervous system that tracks every car's status as it moves through the factory. Each vehicle is assigned a digital build order, stored in a centralized database and updated in real time. This build order contains detailed instructions for every station: which components to install, what software to flash, how to calibrate sensors, and which quality checks to perform. At each workstation, screens display the relevant data for the technician or robot, and barcode or RFID scanners confirm that the correct parts are being used before the system allows the job to proceed. The use of artificial intelligence and machine learning is increasingly embedded into this ecosystem. For instance, predictive maintenance systems monitor vibration, temperature, and performance data from thousands of robots, conveyors, and tools in real time. If a welding robot's arm begins to show early signs of wear, even imperceptible to human operators, the AI flags the issue and schedules preventative maintenance before failure can occur. This predictive approach significantly reduces downtime and helps maintain the tight production cadence that modern car manufacturing demands. Another area where AI plays a pivotal role is in vision systems and quality control. High-resolution cameras paired with deep learning algorithms are used throughout the assembly and inspection processes. These systems are trained on thousands of images to identify correct panel alignment, paint consistency, weld seam quality, and even minute cosmetic defects. In the paint shop, for example, the system can detect a single dust particle trapped in a clear coat, then alert technicians to isolate the cause, whether it's an air filtration issue, static charge on the body panel, or improper cleaning upstream. These insights are logged and used to refine both the hardware and the process over time, feeding back into a continuous improvement loop. But AI is not just about machines replacing human oversight, it's about augmenting human decision-making. In interior assembly, where more variation exists due to trim-level complexity, workers are assisted by augmented reality headsets that project assembly instructions directly into their field of view. These AR systems highlight where each clip, fastener, or electrical connector should go and can overlay 3D models of correct placements onto the physical work area. If the system detects a potential mismatch, such as a left-hand drive HVAC control unit being installed in a right-hand drive model, it alerts the worker before the part is fully installed. This not only reduces errors, but empowers technicians to handle more complex tasks without relying solely on memory or printed documentation. All of these advancements contribute to a concept Volkswagen refers to as smart production, an overarching philosophy that treats the factory not as a static facility, but as a living, evolving system. This philosophy is particularly evident in how Volkswagen manages its energy consumption, materials flow, and human ergonomics. For example, autonomous guided vehicles have largely replaced traditional forklifts and trolleys in many areas of the Golf's production. These AGVs navigate using a combination of magnetic strips, LiDAR, and real-time mapping, delivering parts from storage zones to the assembly line on demand. This reduces congestion, minimizes human error in part selection, and allows the line to adapt more fluidly to shifting production priorities. From an energy standpoint, smart production integrates intelligent building management systems that adjust heating, cooling, and lighting based on real-time occupancy and environmental data. Robots enter standby mode when idle for more than a few seconds. Compressed air systems, traditionally one of the most energy-intensive parts of any industrial plant, are monitored by AI that optimizes pressure delivery to exactly what is needed, exactly where it is needed, with zero excess. These micro-optimizations, when multiplied across thousands of systems and millions of cycles per year, contribute to measurable gains in sustainability. Ergonomics and human factors are also key to this philosophy. Every workstation on the Golf assembly line is designed to reduce strain, fatigue, and injury. Adjustable platforms allow workers to bring the vehicle to an optimal height depending on the task. Overhead, assist arms support the weight of heavy tools, reducing the need for muscle force. Color-coded part trays, automatic torque wrenches, and real-time feedback screens help workers maintain quality while minimizing the mental load of memorizing dozens of process steps. Additionally, Volkswagen invests heavily in worker training, offering digital simulators, VR-based assembly previews, and rotating task assignments to improve skill versatility and maintain high morale. This combination of human-centered design and intelligent automation also allows the Golf production line to be highly responsive to changing market demands. If a sudden spike in orders for a particular trim level occurs, say the Golf GTI with a sunroof and adaptive suspension, the MES system can reprioritize the build queue, notify suppliers of increased part demand, and adjust the workstations along the line in real time. Robots recalibrate their movement patterns, AGVs update their delivery routes, and workers are presented with new instructions through their digital displays. What once would have required days or weeks of retooling now happens in hours, or in some cases, minutes. One of the most compelling outcomes of these systems is Volkswagen's ability to maintain quality parity across global production sites. Thanks to centralized data systems, a Golf built in Wolfsburg can be virtually identical in build quality and performance to one assembled in Puebla, Mexico, or Changchun, China. Volkswagen uses digital twins of its production equipment, virtual replicas that simulate and mirror real-world machines, to replicate best practices across all facilities. If a process optimization is discovered in one plant, such as a more efficient adhesive application method or a faster sensor calibration routine, that improvement can be tested digitally, validated, and then rolled out to other sites via secure updates to their MES software. All of these advancements are not just about building a better car. They're about building a better manufacturing system, one that is scalable, adaptable, and forward-compatible. This is especially important as the automotive industry transitions to electrification. The Golf, as of the latest generation, shares many of its production processes with Volkswagen's ID family of electric vehicles. While the ID.3 and ID.4 are built on a separate platform, MEB. The lessons learned from MQB production, including robot versatility, flexible logistics, and digital calibration, are directly transferable. In fact, many stations within the same factory can now switch between building a combustion engine Golf and an electric vehicle, with only minor tooling changes and software adjustments. Volkswagen's approach to production is ultimately one of modular intelligence, a blend of standardized hardware, reconfigurable software, and scalable systems that can evolve with the demands of new technologies, consumer preferences, and global regulatory changes. And in this sense, every Golf rolling off the line is not just a vehicle, it's a node in a vast, intelligent, and continually learning machine. Our journey begins not with steel or aluminum, but with legacy. Since 1964, the Porsche 911 has set the benchmark for what a sports car can be. Agile, luxurious, powerful, and above all, engineered to the most meticulous standards. The factory that produces this legendary vehicle has been refined and modernized over the years to accommodate new technologies, hybrid integrations, and greater levels of customization, all while preserving the artisanal heart of the brand. Before the first bolt is torqued or the first body panel is pressed, there is data. Every Porsche 911 is built to order, meaning that no two cars are truly identical. Customers choose from an enormous range of exterior colors, wheel types, interior trims, upholstery patterns, drive configurations, and optional performance packages. Each of these selections is encoded into a build sheet, which becomes the digital DNA of the vehicle. This build sheet is fed into Porsche's centralized manufacturing management system. From this point forward, each chassis will be tracked, scheduled, and updated in real time across every workstation in the plant. The first tangible phase of production begins with the body in white construction, which refers to the process of creating the raw, unpainted body shell of the car. In the Porsche 911 factory, the body is built primarily from aluminum and high-strength steel, a marriage of materials that balances rigidity with weight savings. Rolls of sheet aluminum are delivered to the plant and fed into massive hydraulic stamping presses, which operate with pressures exceeding 5,000 tons. These presses form the outer panels of the car, doors, fenders, roof skins, and hoods into their precise curvatures. Each stamping is inspected by laser measurement tools that ensure every contour conforms to Porsche SI's exact specifications, down to fractions of a millimeter. Once all the necessary stamped components are formed, they are sent to the body shop, a cavernous facility where man and machine work side by side. Here, more than 400 industrial robots perform the majority of the welding, riveting, and adhesive bonding. These robots move with uncanny grace and speed, precisely positioning panels and applying structural adhesives or welds with the consistency of a human heartbeat. However, not all tasks are left to automation. Certain weld seams and alignment tasks are still completed by hand, especially those in areas where absolute perfection is required for NVH performance, noise, vibration, and harshness, or where tolerances are too tight for robotic arms to operate without collision. The skeleton of the 911, now taking on its recognizable coupe shape, passes through a series of structural validation checks. Vision systems scan the entire body in white using 3D laser triangulation, capturing a high-resolution digital map of the vehicle geometry. This map is then cross-referenced with the CAD model to identify any deviations. If even a single hole is misaligned or a weld bead is out of tolerance, the vehicle is automatically removed from the line and reworked before proceeding. From the body shop, the chassis enters the paint shop, which is itself a marvel of process engineering. Here, the raw metal body is first subjected to a full chemical cleaning and pre-treatment cycle. It is submerged in a series of dip tanks containing degreasers and anti-corrosion agents, and then it undergoes electrocoating, an electrophoretic process in which an electrical current is passed through the body shell while immersed in a primer bath. This ensures that every crevice, seam, and channel within the structure is evenly coated for rust protection. Once primed, the body passes through a drying oven operating at temperatures of up to 180 degrees Celsius. After cooling, the body is transferred via overhead conveyor to the paint booth. Each booth is a climate-controlled, dust-free chamber where robotic arms, fitted with electrostatic spray heads, apply successive coats of base paint, metallic flakes, and clear lacquer. The electrostatic spray method ensures minimal overspray and maximum efficiency, as the charged paint particles are drawn to the grounded metal body like iron filings to a magnet. Porsche allows for an extraordinary range of exterior colors, and some bespoke configurations can require manual intervention. In these cases, highly trained paint technicians in full-body clean suits step into the booth to manually apply specialty finishes, such as pearlescent or matte paints using handheld spray guns. Between each paint layer, the body is baked and cooled, creating a hardened shell that is both visually flawless and highly durable. The finished result is a surface that must pass microscopic inspection under polarized light to ensure there are no inclusions, orange peel textures, or color mismatches. As the painted bodies emerge from the drying ovens and cool under carefully controlled humidity conditions, they are fitted with temporary protective films to prevent scratches during subsequent assembly stages. These painted shells are then placed onto autonomous guided vehicles, AGVs, that shuttle them silently and efficiently to the final assembly hall, where the true transformation from body to car begins. In parallel to body production and painting, a completely different but equally intricate process has been taking place: powertrain assembly, the heart of every Porsche. 911 is its engine, and this component is assembled in a separate, climate-controlled facility adjacent to the main plant. Whether it is a twin turbocharged flat 6 or a naturally aspirated GT series engine, every unit begins with a bare block, precision machined from a solid billet of aluminum alloy. Each cylinder bore is honed to within microns of its target diameter, and oil channels are cleaned using ultrasonic pulses and compressed air. Engine assembly is a partly manual process performed by specialized technicians who are each responsible for a particular section of the engine. Crankshafts are balanced using laser-guided measurement tools before being seated into their main bearings. Pistons are installed with zero contact to the bore walls, often using air-cushioned insertion tools that prevent even microscopic abrasion. The timing assembly, turbochargers, camshafts, and intake plenums are all mounted with torque-controlled tools calibrated to within a fraction of a Newton meter. Every engine is subject to a dynamic test bench where it is fired up, run through a simulation of driving conditions, and monitored for vibration, oil pressure, thermal behavior, and exhaust output. Only after passing this test is it stamped with its serial number and released to the vehicle assembly line. As the fully painted and protected body shell glides into the final assembly hall on its autonomous guided vehicle, the environment around it becomes a symphony of motion, sound, and precision. This hall is the nexus of the Porsche 911's creation, where everything converges: chassis, drivetrain, interior, electrics, and finishing. The space is brightly lit, immaculately clean, and orchestrated down to the second. Here, automation doesn't replace craftsmanship, it supports it. Skilled technicians and robotic assistants work in tandem, each knowing their roles to an exacting degree. The very first step in this phase is the marriage process, one of the most significant moments in the entire build. This is where the engine, transmission, and rear suspension subassembly, known collectively as the drivetrain module, are bolted to the body. Unlike many front-engine cars, the Porsche 911's signature rear-mounted engine demands a specific approach to alignment and attachment. The powertrain arrives beneath the suspended body shell on a separate carrier, having been pre-assembled and tested in a different wing of the plant. Technicians first conduct a visual and digital verification of the mounting points on both the chassis and drivetrain module. Hydraulic lifts then lower the body shell in slow, controlled increments toward the powertrain unit. At a precise height, robotic torque arms automatically engage the mounting bolts at each corner of the assembly, securing the engine and suspension cradle to the vehicle's rear subframe with surgical precision. Torque specs are logged digitally in the system to ensure that every car meets identical standards. This point is symbolic and functional, the moment the 911 gains its heart. From here, the partially complete car progresses down the assembly line, where the front axle, steering rack, and brake assemblies are installed. These components, like the rear drivetrain, arrive as pre-assembled modules. Porsche's modular assembly system allows highly efficient integration of these parts without slowing the line. The braking system is one of the most advanced in the world, and depending on the configuration chosen by the customer, technicians may install standard steel rotors, larger vented discs, or the elite Porsche ceramic composite brakes. Each caliper is pre-bled and electronically matched to the ABS and stability systems that will later be programmed. As suspension components are torqued into place and the car sits on its wheels for the first time, it travels into the electrical systems installation zone. This is one of the most complex areas in the entire factory due to the sheer density of cabling, sensors, control units, and wiring harnesses that must be routed throughout the body. Unlike conventional vehicles, where looms are installed early, the 911's configuration-specific electronics require precise timing. A team of specialized technicians begins threading the main wiring harness through the firewall, under the dash cross member, along the floor channels, and into the trunk and engine compartments. Multiple electronic control units responsible for engine management, infotainment, lighting, climate control, adaptive suspension, and driver assistance systems are installed along the way. Each ECU is connected and tagged with an identifier, which is scanned into the system to track software compatibility and firmware updates later on. This process involves a blend of manual dexterity and robotic support. Certain harness connections are guided into position by human hands, while robotic arms press connectors into tight sockets with consistent pressure. The system is then subjected to an initial low-voltage power-on sequence to confirm basic circuit integrity. As the car continues down the line, it enters the interior assembly stage, where it truly begins to look and feel like a Porsche. Interior trim parts, such as dashboards, center consoles, seats, door panels, and headliners, are assembled in adjacent cleanroom environments. The level of customization offered for interiors is staggering. Multiple grades of leather, contrast stitching, carbon fiber inlays, Alcantara accents, and rare wood veneers are all possibilities. Each trim package is pre-selected and kitted into an interior build set specifically for the chassis number it will be installed into. The dashboard is one of the first interior components to be fitted. A robotic jig lifts and rotates the dash into the open body shell through the passenger side, where it is then fastened to the front firewall and A-pillar mounts. Once secure, technicians connect HVAC ducts, wiring looms, and install the infotainment screen and gauge cluster. The 911's trademark 5-dial instrument panel is precision calibrated using a laser alignment system to ensure readability and balance. Following this, the central tunnel is installed, anchoring the shifter mechanism, cup holders, and control switches in place. The seating units are next. These are hand-finished in a separate upholstery shop within the factory, where master stitchers work with hides sourced from Northern European cattle farms, chosen for their lower insect scarring due to colder climates. Each seat is sewn, padded, and assembled by hand. Once complete, they are lifted into the cabin using overhead manipulators, then bolted to their mounting rails. Power connections for seat adjustment, ventilation, and memory functions are plugged in and tested on the spot. Following seating installation, door panels, headliners, sun visors, carpeting, and sound insulation materials are methodically added. All of this must be done with extreme care to avoid damage to visible surfaces. Each technician wears custom-fitted gloves and uses tools wrapped in soft plastics to ensure the integrity of every trim surface. As the cabin nears completion, a special quality station is activated where technicians test interior lighting, switchgear function, speaker outputs, and HVAC performance using a diagnostic tablet linked directly to the vehicle's control system. Meanwhile, the exterior finishing process runs in parallel. Pre-assembled elements such as side mirrors, window glass, lights, grills, badges, and bumpers are attached in stages. The front and rear bumpers, painted separately to ensure flawless color match, are fitted using a rail-guided alignment jig that positions each part within a millimeter of its target mounting point. Headlights and taillights are connected and auto-aligned using optical calibration equipment that verifies beam pattern and aim. Next comes the fluid fill stage, where the car receives its essential life fluids: engine oil, transmission fluid, brake fluid, coolant, and refrigerant. Each fluid is dispensed using digitally controlled nozzles that measure exact volumes and record fill data for traceability. The 911's flat 6 engine is particularly sensitive to oil quality and temperature, so the system pre-warms the oil before injection to avoid shocking the internal components. Once all fluids are added, a leak test is conducted using pressure sensors and ultrasonic detectors that can identify even the smallest leak before the vehicle progresses further. The moment the car rolls under its own power for the first time is known as initial startup. At this station, technicians power on the ignition and bring the engine to life. A thick hush falls over the work area as everyone listens intently for any anomalies. The car's onboard diagnostic system runs through a series of checks, monitoring oil pressure, coolant temperature, voltage levels, and sensor outputs. If the car passes this phase, it proceeds to a short drive loop within the factory called the roll test station. In the roll test, the car is placed on a chassis dynamometer, where it is effectively driven at various speeds while remaining stationary. This test simulates road conditions and allows technicians to check gear shifts, brake modulation, ABS function, stability control, steering responsiveness, and exhaust emissions. Sophisticated microphones and vibration sensors placed around the cabin and under the chassis detect unwanted noises or harmonics that might indicate misalignment or defective components. If everything checks out, the car moves to its final quality inspection phase. Here, white-gloved inspectors examine every visible surface of the vehicle under high-intensity lighting in a booth designed to mimic daylight. They look for paint flaws, panel gaps, alignment inconsistencies, and trim defects. Even a single misaligned badge or a fiber of dust under the clear coat can trigger a corrective action. The interior is similarly scrutinized. Vents are tested, buttons are pressed. Leather is scanned for imperfections. As the freshly assembled Porsche 911 completes its final static inspection, it is now ready for the next critical phase, dynamic validation. This is where the vehicle leaves the controlled environment of the assembly hall and is put to the test in real-world conditions, albeit within the carefully designed confines of Porsche's own internal test facilities. Unlike mass-market vehicles that may rely solely on automated testing systems, the Porsche 911 undergoes an extensive series of physical evaluations, driven by human specialists who are trained to detect even the subtlest inconsistencies in performance, feel, and response. The process begins with a water tightness test, sometimes referred to as the monsoon chamber. Each vehicle enters a sealed booth where it is subjected to a simulation of extreme weather. High-pressure jets of water are sprayed from multiple angles, replicating driving through torrential rain, deep puddles, and car washes. The water includes fluorescent dyes, invisible to the naked eye, which are later detected under UV light to identify any intrusion into the cabin or trunk spaces. After several minutes of intense soaking, the car is dried using warm air blowers and checked for leaks or dampness. If the vehicle passes, it is cleared for what many consider the most thrilling part of the production process, the road test. At Porsche's Zuffenhausen facility, a dedicated test track is built into the complex. This closed-loop circuit includes a range of surfaces, elevations, and cornering radii to evaluate every aspect of the 911's performance. Professional test drivers take each car through a series of maneuvers: rapid acceleration, hard braking, slalom turns, rough road surfaces, and steady-state cruising. They listen for abnormal vibrations, dashboard rattles, or drivetrain noise that might indicate improper assembly. Each steering input and suspension reaction is scrutinized. The driver is also watching for proper calibration of the stability management systems, throttle response, gear transitions, and the characteristic mechanical symphony of the 911's powertrain. During this phase, real-time telemetry is streamed from the car to a control center, where engineers monitor data points such as torque delivery, ABS performance, yaw rate, and fuel injection timing. Should any parameter deviate from specification, the car is immediately flagged for corrective adjustment and returned to the factory floor. Once the road test is complete and the car has passed all dynamic performance benchmarks, it is returned to the post-production area for final detailing and preparation. Here, the protective films that were applied after painting are carefully removed. These thin polyethylene sheets have safeguarded the car's painted surfaces throughout the entire assembly process. After their removal, highly trained detailing technicians begin what is often a several-hour procedure to bring the vehicle to showroom condition. Using dual-action polishers, microfiber cloths, and a specialized lineup of Porsche-approved polishers and waxers, they inspect and refine every panel to ensure depth of gloss and clarity of reflection. The interior receives equal attention. Surfaces are dusted, vacuumed, and wiped with non-abrasive cleaners. Fingerprints are removed from touchscreen interfaces, leather is conditioned, and carpets are brushed into uniform directionality. If the car has a convertible top, it is cycled several times to confirm fluid movement and complete sealing. Final torque checks are conducted on exterior trim, wheel bolts, and undercarriage elements. Any last-minute adjustments, such as wheel alignment tweaks or software calibration, are made during this phase. After detailing, the car is moved into the certification bay. Here, its full build record, component scan history, torque log, quality inspection reports, and road test results are compiled into a permanent digital archive linked to the car's VIN. This digital log will remain with the car for the rest of its life and can be accessed by Porsche service centers worldwide. A final multi-point checklist is reviewed by a senior quality engineer. This is a manual review signed off in person, reinforcing the company's philosophy that human craftsmanship and responsibility must coexist with digital precision. Once this final sign-off is completed, the car receives its protective packaging for transport. Soft foam inserts are placed between the tires and the wheel wells to prevent compression damage during shipping. Cloth covers are fitted over the seats, steering wheel, and center console to protect against handling marks. A thick vinyl exterior wrap is then applied over the entire painted surface, including the hood, roof, fenders, and doors. The car is now ready to leave Zuffenhausen, but its journey is only beginning. Porsche's global distribution network is meticulously coordinated from a central logistics hub located on the factory grounds. Each finished vehicle is scanned into the logistics system and assigned to a specific transport route. For cars bound to European dealerships, overland transport by custom-fitted enclosed car carriers is the norm. These trucks are climate-controlled, padded, and outfitted with individual restraint systems to prevent shifting in transit. For overseas markets, including North America, Asia, and the Middle East, the cars are transferred to the port of Bremerhaven, one of the largest automotive export hubs in Europe. En route, they travel by dedicated rail cars equipped with vibration-dampening suspension systems. Each car's location, condition, and shipment status is monitored using GPS trackers and RFID tags embedded in the vehicle's packaging. Upon arrival at the port, the vehicles are unloaded into secure storage lots, awaiting roll-on, roll-off vessel boarding. Porsche does not allow external drivers to handle the vehicles. Instead, factory-certified personnel drive each 911 onto the ship's internal decks, where they are secured using specialized harness systems. The shipping containers are climate monitored, and their humidity levels are controlled to prevent corrosion or material degradation during the voyage. Some regions with extremely sensitive climates, such as tropical zones or high humidity areas, require an additional layer of desiccant packaging and underbody protection. Once the cars arrive in their destination country, they are typically routed through a regional Porsche distribution center. These centers conduct a pre-delivery inspection or PDI. During this process, shipping materials are removed, fluid levels are rechecked, tire pressures are set to local spec, and country-specific features such as local language infotainment systems, navigation maps, and compliance labels are configured. The battery, which may have been put in shipping mode during transit, is recharged and tested. Only once the car clears this PDI is it finally released to the dealership. At the dealership level, the car undergoes one final cosmetic inspection before being presented to the customer. If a customer has ordered their 911 through Porsche's exclusive manufacturer program, this delivery often includes a ceremonial handover in a private lounge, with factory personnel available to walk through every detail of the vehicle's features. In some cases, particularly in Europe, customers can even take delivery at the factory itself, where their car is unveiled in a glass-walled rotunda with dramatic lighting, followed by a first drive on scenic roads around Stuttgart. Yet even after delivery, the role of the factory is not quite over. Thanks to Porsche's connected car architecture, many vehicles are capable of over-the-air updates that improve performance, add new features, or correct bugs discovered in the field. Data collected during actual driving, such as engine behavior, brake wear, and climate control usage, is anonymized and fed back to Porsche's research and development teams to inform future designs and calibrations. It's a feedback loop that allows every Porsche built today to contribute to the improvement of the next generation. Meanwhile, back at Zuffenhausen, production continues. Every morning, a new batch of orders is passed into build sequences based on available component inventory, production capacity, and shipping schedules. Hundreds of thousands of individual parts must be delivered to the exact right station at the exact right time to maintain flow. This is made possible through a just-in-time logistics strategy, supported by automated material handling systems and a synchronized supplier network. Some high-value or rare components, such as carbon ceramic brake rotors or forged aluminum wheels, are flown in daily from satellite facilities or specialist subcontractors. The factory itself operates with a level of sustainability and energy efficiency that reflects the future of manufacturing. Solar panels line the roofs, producing a significant percentage of the plant's electricity. Rainwater harvesting systems supply grey water for cleaning and HVAC cooling. Waste heat from the paint ovens is recirculated to warm other parts of the facility, and zero waste policies ensure that unused materials are either recycled or repurposed. Even the autonomous transport carts that move parts and vehicles between stations run on battery power, coordinated by an AI-powered logistics brain that continuously optimizes paths and traffic flow. By the time a single Porsche 911 is completed and delivered to its owner, it has passed through the hands of more than 1,500 people, touched over 3,000 unique components, and been subjected to hundreds of quality checks and dozens of performance tests. Every detail, from the composition of its alloy wheels to the grain of its leather, has been examined, tested, and refined to deliver the unified experience that the 911 is known for. Inside the Zuffenhausen facility, what stands out most, beyond the hum of machinery and gleam of painted panels, is the harmonious integration of advanced automation with human craftsmanship. While much of the modern automotive world has shifted heavily toward fully robotic production lines, Porsche has taken a more balanced approach. It is this hybrid system, where intelligent machines handle precision tasks and highly trained specialists deliver the emotional and tactile elements, that makes the production of the 911 so uniquely effective and true to its heritage. To understand the depth of Porsche's production system, we need to go deeper into the factory automation architecture that supports every step of the process. Central to this is the Manufacturing Execution System, or MES. This digital control layer connects every workstation, tool, robot, and technician across the plant in real time. From the moment a customer's order is locked in, a virtual avatar of that specific car is created within the MES. This avatar tracks everything: colors, materials, powertrain choices, region-specific requirements, and optional extras, and constantly relays this data to the precise equipment or technician that will handle each part of the build. In the chassis assembly line, for example, if a customer has ordered rear-wheel steering and adaptive PASM suspension, the MES sends signals to the automated picking system to retrieve the correct components. A robotic arm pulls these from storage bins, places them into a bin or cart customized for that vehicle, and tags it with the car's digital signature. The cart then travels on a guided track to meet the body shell exactly as it arrives at the workstation. At no point is there ambiguity or lag. Everything is orchestrated by this unseen digital conductor that ensures every worker and every robot knows exactly what to do for every unique build. Beyond simple part logistics, Porsche's MES also controls robot behavior, torque tools, and environmental systems. Take the example of robotic arms applying sealant to the underbody and joints of the car. These robots receive precise instructions on bead width, viscosity compensation, path mapping, and cure time, all tailored to the ambient humidity and temperature at that exact moment. If conditions drift even slightly out of tolerance, the system adjusts on the fly. If a deviation is too great, the system pauses the robot and calls for human review. This level of responsiveness ensures not only uniform quality, but a kind of built-in vigilance that prevents minor errors from becoming major issues downstream. Nowhere is this marriage of automation and craftsmanship more evident than in Porsche's exclusive Manufaktur department, a special division within the factory dedicated to bespoke customization. Here, human hands reign supreme. Customers who opt for this level of personalization can request everything from custom mixed exterior colors to leather-trimmed air vents, contrast-stitched seatbelts, or brushed aluminum door sills engraved with their name or family crest. These options cannot be installed by robots. They demand skilled labor, patience, and a deep understanding of materials. For instance, if a customer chooses deviated stitching in a rare color like Guards Red on a graphite interior, that thread is sourced separately, wound into bobbins, and installed on special industrial sewing machines operated only by master upholsterers. Each stitch line must be perfectly parallel and uniformly tensioned. The leather pieces are cut using high-frequency oscillating blades controlled by software, but the actual alignment and mounting onto trim pieces is done manually, using a keen eye and muscle memory developed over years of experience. Even more exclusive are options like natural wood inlays, which are created by slicing extremely thin veneers from selected timber, pressing them onto aluminum substrates, and hand finishing them with lacquer, polishing, and oiling processes. Because natural wood grains are unpredictable, no two trim sets are alike, and each must be evaluated for visual balance and grain orientation by an expert before being installed. Moving to another area of innovation, we find the powertrain production of the 911 continuing to evolve alongside the rest of the industry. While Porsche remained steadfast in its commitment to the internal combustion engine, particularly the legendary Flat 6, it has also begun preparing for a future that involves greater electrification. Already, hybrid-ready architectures are being integrated into the production lines, and new high-voltage testing bays have been built to accommodate future variants. The current engines are built in a separate but nearby facility that operates with a clean room-like atmosphere. Every engine builder works at a station equipped with digital torque wrenches, oil mist extractors, and real-time visual feedback displays. These displays show exploded diagrams of the current build, torque values required for each bolt, and any sequencing constraints. This allows even complex assemblies, such as the twin turbocharged air intake plenum or variable cam timing modules, to be installed with absolute accuracy. Each engine is assembled in a vertical build sequence, meaning it remains upright throughout the process to reduce the risk of contamination or misalignment. Oil galleries and cooling jackets are cleaned with pulsed air systems and inspected with endoscopic cameras before being sealed. Once complete, the engine is placed on a mobile test rig, where it undergoes a cold test cycle, rotated via electric motors without fuel ignition to measure resistance, internal pressure differentials, and sensor behavior. Only after passing this does it proceed to hot testing on a dynamic dyno bench. The dyno bench is a marvel in itself. Each engine is connected to a computer-controlled load cell and run through a simulated break-in process. Sensors record everything: oil pressure fluctuations, exhaust lambda values, detonation signatures, and even the sound frequency of valve operation. The engine is revved, held under load, cooled, and restarted multiple times. Only when it has performed flawlessly under all conditions is it released and stamped with a code that matches it permanently to a specific chassis. Returning to the factory floor, the final fit and finish phase is where Porsche's obsession with detail truly shines. One area of particular focus is panel alignment and gap consistency. Unlike volume manufacturers, where acceptable tolerances for panel gaps can vary by several millimeters, Porsche targets consistency within less than half a millimeter. Each door, hood, and trunk lid is mounted loosely at first, then adjusted using laser-guided tools and feeler gauges. Special brackets hold the panels in place while final torques are applied. This is not just for aesthetics. Precise gaps reduce wind noise, improve aerodynamics, and enhance door closing feel. Sound is another key dimension. Engineers at Porsche place heavy emphasis on acoustic tuning, not only of the engine and exhaust, but also of the cabin itself. During development, microphones are embedded in prototype vehicles and driven through tunnels, highways, and cobblestone streets to capture all forms of noise, resonance, drumming, creaks, and wind intrusion. The data is used to inform production processes such as body seam sealing, insulation placement, and even the thickness of laminated glass. Once in production, these same noise benchmarks are monitored. If a particular car emits even a slightly louder door rattle than expected, it is pulled for correction. Climate performance is also evaluated under extreme conditions. Select vehicles are placed inside thermal chambers that simulate environments from Arctic cold to desert heat. Inside, engineers test HVAC operation, defrost speed, material expansion behavior, and adhesive bonding under thermal stress. Porsche uses infrared cameras to study heat distribution inside the cabin and applies this information to optimize vent design and airflow management. Finally, we must acknowledge the human element, the thousands of workers and craftspeople who bring each 911 to life. At Zuffenhausen, training is rigorous. Every new technician undergoes months of apprenticeship, not just in tool use or station procedure, but in the philosophy of Porsche manufacturing. This includes historical education on past models, design language, customer expectations, and a deep respect for the badge each vehicle will wear. Quality auditors rotate through various departments, performing random checks, coaching less experienced colleagues, and updating work instructions when issues arise. Continuous improvement is part of the culture, and feedback loops from dealerships and customer surveys are studied and integrated into daily operations. It's not uncommon for production processes to be revised weekly, not because something went wrong, but because something could be done just a little better. Our journey begins deep within the steel supply and stamping operations, far from the glittering finish lines of final inspection. The G-Class starts life as a collection of raw, flat metal panels. These panels, primarily high-strength steel, are delivered to the facility in massive coils, which are unrolled and leveled before being fed into industrial press machines. These presses apply thousands of tons of pressure to shape the steel into the various foundational parts of the G-Class body, such as the floor pan, door skins, roof frame, and iconic flat body panels. The unibody shell is not used in the G-Class. Instead, it's built with a ladder frame chassis, a method more common in heavy-duty trucks. This makes the process both more rugged and more complex, requiring each piece to be perfectly formed to exact tolerances. Once the panels are pressed, laser-guided robotic arms trim and smooth the edges with astonishing precision. Each cut is planned digitally down to the 1/10 of a millimeter, ensuring uniformity across thousands of units. Now we move into the body in white phase, the initial stage of structural assembly. Here, the stamped panels are arranged into sub-assemblies. The floor pan, side frames, firewall, and roof supports are meticulously aligned on a series of jig fixtures. These large, articulated steel mounts hold each piece in perfect position for welding. But unlike many modern car factories where robot arms zip through spot welds in a blur, the G-Class body is largely welded by hand. Dozens of skilled technicians, each highly trained, wield welding torches in a choreographed dance of sparks and heat. More than 6,000 welds are performed on each body, reinforcing the vehicle's structural rigidity. As they go, workers constantly inspect joints visually and mechanically, using go-no-go gauges to confirm tight fits and ensure that structural integrity is never compromised. The welding process is a symphony of patience and expertise. Welders must account for heat distortion, managing the order and location of each weld to maintain the geometric accuracy of the body. They use pneumatic clamps, steel rulers, and laser levels to ensure that the angles and lines of the body remain true. It is here that the G-Class's signature upright posture begins to take shape. Those vertical window frames, slab-sided doors, and angular corners that give the vehicle its commanding silhouette. They're all defined and locked into place during this early phase. Once the body is fully welded and structurally complete, it undergoes a process known as metal finishing. This is where skilled craftsmen examine every seam, edge, and panel for imperfections. Small hammers, abrasives, and filler tools are used to smooth out inconsistencies. The goal is to achieve a surface that will accept paint without a single visible ripple or deformity. The attention to detail here is extraordinary. What may seem like an invisible bump to the naked eye will be caught later by paint defects if not resolved. Technicians in this stage often use high-powered overhead lights and fingertip inspection techniques to feel for irregularities. And yes, they still do it by touch. Technology can detect misalignments, but it's the trained human hand that often finds the smallest flaws. Once the body in white has passed inspection, it is ready for paint preparation. But before any color is applied, the shell undergoes a rigorous cleaning process. It is first immersed in a series of chemical baths, alkaline cleaners, degreasers, and deionized water rinses that strip away all traces of oils, residues, or contaminants from the welding and finishing stages. Then it moves into the e-coating process. This is where the body shell is dipped into a giant electrocoating tank filled with anti-corrosion primer. An electrical current is applied, causing the primer to bond to the metal surface at a molecular level. Every nook, crevice, and corner is coated evenly, providing unmatched rust protection. The G-Class was originally built for military duty, and this durability-focused philosophy continues today. After the e-coating, the body is cured in an oven at temperatures around 180 degrees Celsius. The curing hardens the primer and sets the foundation for the paintwork that will follow. Then comes the application of the base coat, color layers, and clear coat, each sprayed meticulously in high-tech painting booths. The factory offers a broad range of colors, from conservative blacks and silvers to vibrant custom finishes from the G Manufacture Personalization Program. Incredibly, many G-Class vehicles receive their paint by hand spraying, not automated robots. This allows greater control and customization for two-tone finishes, matte effects, and hand-masked accents. The painted body then returns to another round of inspections. Factory workers use light tunnels and soft cloths to detect even the smallest specks of dust, paint sagging, or orange peel textures. If needed, technicians wet sand and polish the affected areas manually. This is one of the most time-consuming parts of the process, but it ensures that the G-Class leaves the paint shop with a flawless, mirror-like surface. With the body now painted and prepped, attention turns to the chassis, the rugged ladder frame that defines the G-Class's off-road DNA. Unlike unibody cars, where the structure and body are fused, the G-Class separates these two elements, a design that offers superior strength and modularity. The chassis is fabricated from thick-gauge steel and welded into a rectangular framework with multiple crossmembers and mounting points. It's engineered to endure extreme torsional loads from uneven terrain, rock crawling, and high-speed travel over unpaved surfaces. The entire chassis is then treated with a special powder coating that protects it from gravel, salt, moisture, and mechanical wear. At this point, the chassis begins its mechanical assembly. Giant overhead conveyors lifted into place on a moving assembly line. Suspension components are added first. The G-Class uses a double wishbone front suspension and a rigid rear axle with trailing arms and coil springs, all designed for articulation and ride comfort. Workers mount control arms, install air or coil springs depending on the configuration, and torque each fastener to precise specs using digital torque wrenches that record every application for quality traceability. Drive shafts, differentials, and the transfer case follow next. The G-Class features 3 locking differentials, front, center, and rear, making it one of the most capable factory off-roaders ever built. These components are pre-assembled in sublines and arrive at the main chassis line just in time for installation. Each differential is bench tested before being mounted, and once installed, hydraulic and electronic connections are secured and checked for sealing integrity. Next, the engine and transmission arrive. These powertrains are built separately, typically at Mercedes powertrain facilities, and delivered fully dressed with wiring harnesses, fuel systems, and control modules already in place. A robotic hoist lowers the engine and transmission into the chassis as technicians bolt it down to reinforced subframe mounts. The transmission tunnel is lined with heat shielding and the exhaust system is connected, stainless steel manifolds, catalytic converters, and mufflers are all aligned with laser guidance systems to ensure proper clearance and vibration isolation. As the powertrain is secured, attention turns to the braking and steering systems. High-performance disc brakes with multi-piston calipers are installed on each wheel hub. Brake lines are routed with stainless steel fittings and then bled using automated vacuum machines to ensure a perfect seal and no air bubbles. The power steering rack is attached and aligned, and its fluid circuits are pre-flushed to remove any contaminants. At this stage, the chassis is essentially a rolling platform, ready to meet the painted body that has been traveling in parallel on a separate line. Continuing our journey into the heart of the Mercedes-Benz G-Class assembly process, we arrive at the moment of mechanical matrimony, a pivotal point known within the factory as the marriage. This step is one of the most anticipated stages in any automotive plant, but here in Graz, it carries almost ceremonial weight. The moment when the meticulously painted body is lowered onto the fully built ladder frame chassis transforms a collection of high-grade parts into what begins to truly resemble a finished G-Class. The process begins with both the body and the chassis arriving at the marriage station on two separate automated conveyor lines. Precision and timing are essential, as the chassis is lined up beneath the suspended body shell. A series of hydraulic lifts and alignment pins begin the delicate work of bringing the two together. Technicians verify multiple reference points using laser measurement tools to ensure the body mounts align perfectly with the corresponding points on the chassis. The process may appear straightforward, but in reality, the tolerances are extremely tight, within a single millimeter. Any deviation could lead to misaligned panels, noisy interiors, or handling inconsistencies. Once the alignment is verified, the body is carefully lowered using a multi-axis robotic gantry system. Specialized bushings are inserted between body and frame to absorb vibrations, and bolts are torqued down using synchronized electric torque tools. These tools not only apply the correct force, but also record each torque event digitally for traceability. In total, dozens of mounting points are secured during this stage, creating a permanent bond between body and chassis. With the vehicle now structurally complete, the next steps shift focus to the installation of electrical systems and interior components. The G-Class is known for its advanced technology, luxury appointments, and off-road capability, all of which require an intricate network of electronics. Wiring harnesses are delivered to the line pre-assembled and bundled according to specific vehicle configurations. Each harness includes connectors for power distribution, lighting, infotainment, sensors, airbags, and the drivetrain management system. Installation of these harnesses is done mostly by hand due to the complexity and variability of options in each vehicle. Workers snake thick bundles of cables through the body structure, routing them through the firewall, behind the dashboard frame, under the floor, and along the roof rails. Clamps and cable guides ensure the wiring remains secure and doesn't rattle or chafe over time. Diagnostic computers are connected at this stage to confirm continuity, check for shorts, and verify module communications over the vehicle's CAN bus network. While this is happening, the HVAC system is assembled and installed. This includes the heater core, evaporator unit, blower fans, and electronic control motors that adjust airflow and temperature zones. The G-Class features multi-zone climate control, so ducting is routed with exacting precision through the dash, footwells, and rear cabin areas. Once the climate system is in place, the dashboard sub-assembly is installed as a single module. This enormous component includes the infotainment screen, control buttons, ambient lighting strips, and the central air vents. Workers use vacuum suction lifts to guide the dash into place without damaging the painted surfaces or soft leather trim. Now comes one of the most craftsmanship-intensive stages in the entire production, the installation of the interior. Unlike many mass-produced vehicles that use synthetic fabrics and machine-mounted panels, the G-Class is fitted largely by hand, using real materials: leather, wood, aluminum, and piano black lacquered plastics. The seats are built separately and upholstered using hides that are individually inspected for imperfections. Skilled trimmers sew the leather together, using double stitching patterns that match the exterior color or the customer's specification. Once finished, the seats are bolted into the vehicle with electronic seat module calibration to ensure proper memory function and lumbar support. Door panels follow next. These are assembled in parallel stations where components like speaker grills, switches, ambient lighting, and leather inserts are bonded together before being mounted. Each panel is carefully pressed into place and tested for fit, sound insulation, and tactile feedback. The sound of a G-Class door closing is legendary, an unmistakable mechanical clunk that speaks to solidity. Achieving this sound requires a precise interplay of hinges, rubber seals, door weight, and locking mechanism geometry. Carpeting, floor mats, headliners, and trim moldings are next. Workers stretch and press these components into place using heat guns and hand rollers to ensure wrinkle-free surfaces and tight fits. The sunroof assembly is dropped in from above and sealed with multi-layer gaskets to prevent leaks. All the while, every stage includes quality inspections using both visual checks and functional tests. Is the stitching even? Does the infotainment system respond instantly to input? Is the rear seat heating element warming to spec? These aren't afterthoughts, they're checked and verified at every step. With the interior mostly complete, attention now turns to the installation of exterior finishing components. This includes the lighting systems, trim pieces, bumpers, grills, and the wheels and tires. Headlights and taillights are delivered in sealed packaging and installed using torque-controlled tools to avoid over-tightening. Each lighting unit is powered on and subjected to an alignment procedure that ensures optimal beam projection. The G-Class often includes LED matrix lighting, so precise calibration is required to ensure adaptive lighting functions correctly on the road. The bumpers, both front and rear, are more than decorative. They contain impact absorbers, parking sensors, and, in some models, radar modules for adaptive cruise control. These systems must be aligned with the vehicle's central ECU and tested for accuracy. The grille, which houses the iconic Mercedes three-pointed star, is mounted next, followed by trim pieces such as side skirts, fender flares, and the protective body cladding that's especially important for off-road variants. Wheels and tires are mounted towards the end of this phase. Each tire is balanced individually before mounting to minimize road vibration. The G-Class uses either 18-inch or larger wheels, depending on the model, and all are fitted with performance all-season or off-road tires. Lug nuts are torqued in a star pattern and then double-checked by a second technician for safety. The signature rear-mounted spare wheel is added last, requiring special reinforcement brackets to support its considerable weight. At this point, the vehicle is externally and internally complete, but it hasn't yet proven itself ready for the road. That's where the end-of-line testing begins. First, each vehicle is rolled onto a chassis dynamometer for a systems check. This stationary rolling road allows technicians to simulate driving conditions without the vehicle leaving the factory. Engines are started and revved through a range of RPMs. The transmission is cycled through its gears. Braking systems are tested under controlled load. Onboard diagnostics scan every system for fault codes, and calibration values are adjusted in real time. Next, the G-Class is taken into the water testing booth, a sealed chamber where high-pressure water jets blast the vehicle from all angles. This simulates heavy rainfall and river fording to confirm that all seals and gaskets are intact. Doors, windows, the sunroof, and even antenna mounts are tested for ingress. Any leaks are flagged for immediate remediation. Following the water test, vehicles are subjected to a visual inspection tunnel with multi-angle lighting. Here, inspectors walk around each unit, examining body panel gaps, paint reflections, wheel alignment, and emblem placement. Mirrors are adjusted, wiper blades tested, and final protective films removed. Finally, the G-Class is driven onto a short test track either inside or just outside the factory. This final road test includes a variety of surfaces: cobblestones, incline ramps, sharp turns, and slalom sections. Trained drivers listen for abnormal noises, feel for steering alignment, and evaluate ride quality. Any deviation from spec sends the vehicle to a special adjustment area for corrections. Only once all tests are passed does the vehicle receive its final factory seal of approval. Even then, however, the process isn't over. Depending on the destination, additional country-specific requirements are installed. These may include compliance labels, GPS regional settings, localized safety equipment, and left or right-hand drive adjustments. Paperwork is finalized, including the build sheet, quality inspection records, and shipment documentation. The vehicle is then either driven onto a covered transport truck or loaded into a sealed container for overseas shipping. Now that the G-Class has completed its rigorous in-factory berth, a process involving welding, painting, assembly, and exhaustive quality checks, it embarks on the next critical phase of its journey: preparation for global distribution. This phase, though less visually dramatic than robotic welders or precision-aligned dashboards, is nonetheless a feat of coordination and logistics. The moment a G-Class rolls out of the Magna Steyr facility in Graz, Austria, it transitions from handcrafted engineering marvel to a globally positioned product, bound for showrooms, private collections, mountain trails, or inner-city avenues. But before it reaches any of these, there is still a tremendous amount of effort that goes into protecting, staging, and transporting each unit with the same care and attention to detail used in its creation. Once a G-Class vehicle has passed its final road test and received its full quality release documentation, it is driven under its own power to the staging area adjacent to the main plant. Here, specially trained logistics personnel begin the final detailing and protection process. Although the vehicle is fully finished, there is a layer of preparation necessary to ensure it survives the rigors of global shipping. Protective films are applied to sensitive areas: the hood, roof, door sills, mirrors, and corners of the bumpers are covered with temporary plastic guards that resist scratches, UV exposure, and road grime. The alloy wheels are often wrapped in foam liners or protective rings to prevent damage from transport straps or accidental impacts during loading. Interior surfaces are also shielded with plastic covers over the seats, infotainment screens, and floor mats. Every vehicle is now tagged with a unique, VIN-linked logistics barcode, which details its destination, shipping method, port of entry, and delivery window. This data is integrated with Mercedes-Benz's global tracking system, allowing every stakeholder, from plant logistics to overseas dealerships, to monitor the car's location in real time. Depending on its final destination, the G-Class may undergo additional region-specific programming. For example, a vehicle bound for North America will be loaded with US-specific emissions calibrations and compliance documentation, while one heading to the Middle East might receive enhanced climate control settings and reinforced dust filtration for desert conditions. Next, the vehicle is routed to one of several outbound transport modes. For European customers or regional delivery, G-Classes are typically driven onto covered car haulers, large multi-deck trucks designed to transport 6 to 8 vehicles at a time. These trucks have air ride suspensions to reduce vibrations and protect the delicate ride height sensors and chassis calibration. For vehicles headed abroad, the process is more elaborate. The G-Classes are driven into rail cars or loaded into intermodal shipping containers, which are then routed to seaports like Bremerhaven in Germany or Koper in Slovenia. At the port, each container or open deck vessel is handled with specialized cranes and ramps that minimize jostling. It is worth noting that many G-Class models, particularly Special Edition or G Manufaktur builds, are transported in sealed containers to prevent salt spray, sun fading, or theft. The voyage by sea can take several weeks. For example, vehicles headed to North America might pass through the English Channel, cross the Atlantic, and dock at ports like Baltimore or Brunswick. Once at port, they are processed through customs, emissions, and safety verification, all under the oversight of Mercedes-Benz regional distribution centers. Then comes a second round of quality control, sometimes called a PDI or pre-delivery inspection. This includes checking tire pressure, recalibrating navigation systems to the local GPS constellation, adjusting language and date formats, and inspecting the vehicle for any damage incurred during shipping. If a vehicle has traveled thousands of kilometers by rail, truck, and sea, this inspection is crucial to maintain the brand's reputation for perfection. Once cleared, the G-Class is dispatched to its final destination: a dealership, fleet customer, private buyer, or regional collection center. Even here, the aura of exclusivity surrounding the G-Class continues. Many buyers opt for specialized white glove delivery, wherein the vehicle is transported by single-car covered trailer and presented with ceremonial fanfare, unveiling cloth, branded key boxes, and sometimes a personal orientation session with a brand specialist. The delivery experience is designed to match the vehicle's pedigree, but beyond the logistics and visual pageantry, what truly makes the G-Class remarkable is that even after all of this effort, the vehicle is still, at heart, a rugged, off-road tool. Every single G-Class, whether destined for a downtown penthouse or a mining operation in Siberia, is built to the same foundational spec: full-time four-wheel drive, locking differentials, a 2-speed transfer case, and a ladder frame that could survive military deployment. That's the irony and the charm of the G-Class. It's capable of climbing a 45-degree incline, fording rivers, and navigating icy switchbacks, yet it will just as often be used to roll quietly over cobblestones in Monaco or park beneath luxury boutiques in Dubai. The factory doesn't know what fate awaits each G-Class, and it doesn't matter. Each one is engineered for extremes, regardless of how pampered its life may be. Now, let's take a moment to consider the people behind this machine. While many modern automotive factories are fully robotic and optimized for scale, the G-Class production line retains an unusually high proportion of human labor. Over 1,500 skilled workers at Magna Steyr contribute to its assembly, many of them having decades of experience with the model. Their knowledge, much of it gained through repetition, mentoring, and attention to the tactile feedback of materials, is irreplaceable. They know the right torque by feel. They can spot a millimeter-wide gap from across the room. In a time where artificial intelligence and robotics are reshaping the manufacturing landscape, the G-Class stands as an example of how artisanal skills still hold tremendous value. This blend of traditional craftsmanship and modern precision engineering is particularly evident in the G Manufaktur program. Here, customers can personalize nearly every aspect of their G-Class, from more than 30 exterior paint killers to a wide range of leather hues, stitching patterns, interior trims, and wheel designs. If a buyer wants orange leather with green piping and a matte olive exterior, they can have it. These builds are not separated into another facility. They're integrated into the main production line with designated bays where craftsmen apply these one-off features by hand. This level of customization presents huge logistical challenges, matching materials to build slots, keeping non-standard parts in stock, and maintaining quality across thousands of permutations. Yet the factory has embraced this complexity as a way to deepen the bond between owner and vehicle. Meanwhile, let's not forget the rigorous quality control that continues to influence every element of the G-Class's construction. For example, every powertrain used in the G-Class, whether the twin turbocharged V8 in the AMG variant or the inline-6 in the standard model, undergoes cold testing prior to installation. In cold testing, engines are spun up using electric motors without firing them, while sensors measure oil pressure, bearing resistance, valve timing, and sealing. This ensures that only powertrains meeting exact tolerances make it to the assembly floor. Similarly, each differential assembly is bench tested for noise and balance before integration into the vehicle. It's not enough for components to fit. They must perform to exacting standards. Even paint color undergoes scientific scrutiny. After application, each painted body is checked using spectrophotometers, special instruments that detect even the slightest variation in hue, brightness, and saturation. This is especially important when replacing panels after damage or repair. Consistency in color across different batches of paint and lighting conditions is notoriously difficult. Yet, Mercedes insists on millimetric perfection, even for colors that might only be chosen by 1 in 1,000 customers. It's this obsessive attention to detail that makes the G-Class stand out, and it's why its production process is stretched over more than 100 hours per vehicle. Where other vehicles are designed for efficiency, the G-Class is designed for excellence. Every step, from welding to upholstery, from software calibration to final wheel alignment, is geared toward creating something more than just a car. It's a statement of what happens when engineering, tradition, and passion come together under one roof. The story of the Škoda Octavia begins long before a single bolt is fastened or a robotic arm glides into action. It begins, in fact, with an idea, a blueprint forged in design studios, simulated on computers, and tested in virtual environments by engineers who must balance performance, efficiency, safety, and style. But for our purposes, the journey begins at the factory, where engineering dreams are translated into industrial reality. Welcome to the highly synchronized and precision-driven world of Škoda Octavia production. Every Octavia starts as raw material, high-strength steel coils delivered to the plant by rail or truck, sourced from carefully vetted metallurgical suppliers across Europe. These coils are massive, weighing several tons each, and are stored in a specially climate-controlled steel depot on the factory premises. Before they even reach the production line, each coil is identified with barcodes, batch numbers, and chemical composition data. Technicians conduct tensile strength and thickness tests to ensure the material meets Škoda's exacting standards. Once approved, these steel coils are fed into the blanking line, an automated system that unrolls, flattens, and cuts the steel into large sheet panels. This is no ordinary cutting process. A high-speed hydraulic press slices the sheets using dies that match each specific component, from door frames to hood panels. The accuracy here is down to tenths of a millimeter. Each sheet is then stacked in order, transported by robotic forklifts to the body shop, where one of the most visually captivating segments of production begins. The body shop is a symphony of automation. Over 600 industrial robots, mostly 6-axis KUKA robots, work with millimeter-level accuracy to build what's known as the body in white, the skeletal structure of the Octavia. Here, robotic arms pick up the steel panels and place them into precision jigs. Another set of robots joins them using spot welding. More than 5,000 weld points are applied to a single body shell, each weld carried out in fractions of a second. Sensors within the robots constantly monitor heat, pressure, and positioning to ensure perfect fusion every time. At this point, the vehicle starts to resemble a car, but just barely. The body is incomplete and fragile, still lacking reinforcements, internal frames, and roof components. The roof is attached next, along with the inner structures of the door frames and A-pillars. This structural framing phase is crucial as it determines the vehicle's crashworthiness and rigidity. Škoda uses high-strength boron steel reinforcements in critical areas such as the B-pillar to enhance passenger protection during side impacts. To ensure dimensional accuracy, every fifth body in white is routed to a coordinate measuring cell, an enclosed chamber with laser scanners and mechanical probes that measure thousands of points across the body. Any deviation outside the strict tolerances prompts a quality control response, sometimes resulting in real-time die adjustments or jig calibrations on the production line. With the structural shell now complete, the body is moved via an overhead conveyor system to the next phase, the paint shop. But before any paint can be applied, the shell undergoes one of the most chemically intensive processes in the factory, the pre-treatment line. Here, the body is dipped into a series of 12 to 14 baths, starting with alkaline cleaners that strip oils and residues from the welding process, followed by zinc phosphate baths that apply an anti-corrosion layer at the molecular level. This immersion is done using a massive rotodip system, which rotates the entire body in white 360 degrees in giant tanks, ensuring every surface, cavity, and seam is fully treated. After rinsing and drying, the shell enters the electrocoating tank, where an electrical current is passed through a special primer solution. The car body acts as a cathode, attracting the primer particles, which adhere uniformly even inside tiny crevices. This electrophoretic coating forms the first of several protective paint layers. From here, the body moves into sealed spray booths where automated sprayers apply multiple coats of paint, typically a base coat for color and a clear coat for gloss and UV protection. The environment inside these booths is tightly controlled. Temperature, humidity, and air pressure are constantly monitored to prevent dust intrusion or paint imperfections. Any deviation can lead to paint defects like orange peel or fisheyes, which are not tolerated on the line. Once painted, the shell is moved into a high-temperature oven or curing oven, where it is baked at around 150 to 180 degrees Celsius for up to 30 minutes. This curing process chemically bonds the paint to the metal, hardening it into a resilient shell. After cooling, a small team of human inspectors examines each body under specialized lighting tunnels, checking for the slightest flaws in gloss, color uniformity, or texture. Any imperfection, no matter how small, is flagged, buffed, or resprayed. Next, the painted shell enters what is known as the trim and final assembly area, arguably the most complex and human-intensive part of the production line. It's here that the skeletal shell of the Octavia transforms into a functional vehicle. The doors are removed temporarily and sent down a separate subline for internal fitting. This allows easier access for workers and robotic systems to install key internal components like dashboards, wiring harnesses, HVAC units, and center consoles. The main body, now called the marriage body, proceeds on a conveyor to the cockpit station. Here, large sub-assemblies, pre-assembled in adjacent areas of the factory, are carefully fitted into place. The dashboard unit, including instrument clusters, infotainment systems, and climate controls, is mounted in one seamless motion using a robotic assist arm designed to handle sensitive electronic modules without damaging connectors or wiring. Wiring harnesses, which serve as the car's nervous system, are routed throughout the body with meticulous care. These harnesses contain dozens of bundled cables, each color-coded and tagged for correct routing to lights, sensors, powertrains, and control modules. Workers follow digital torque instructions via handheld screwdrivers with built-in sensors that alert them to any over or under tightening of critical fasteners. Every step is logged digitally to ensure traceability down to the individual component level. At this stage, the car receives its interior features: carpeting, seats, airbags, and insulation. The seats themselves arrive as complete modules, built in a just-in-time fashion by nearby suppliers and delivered to the line by autonomous mobile robots. Each seat is barcoded and matched to the specific configuration of the car: cloth or leather, heated or ventilated, manual or power adjusted, and installed in one swift but carefully measured motion. As the Škoda Octavia's skeletal structure is now fully formed, painted, and partially assembled with its interior trim and wiring infrastructure in place, the process turns toward one of the most crucial phases of all: the marriage of the car body with its drivetrain and chassis. This stage is where the Octavia transitions from a lifeless shell into a machine capable of movement, energy, and direction. The drivetrain, consisting of the engine, transmission, front and rear axles, and various suspension components, is assembled separately in a highly organized and synchronized subline known as the powertrain line. This area operates like a standalone microfactory, complete with its own logistics network, inspection checkpoints, and robotic assistance. Engines are delivered from Škoda's engine plant, typically either turbocharged TSI petrol or TDI diesel configurations, though plug-in hybrid variants also have their own specialized integration procedures. These engines arrive as complete units, fully tested, barcoded, and preloaded with essential fluids. Upon arrival, the engines are mounted onto steel cradles, also called front-end modules or subframes, where additional components such as radiators, electric fans, intercoolers, and sometimes the front suspension wishbones are attached. At the same time, transmission units, whether manual or DSG dual-clutch gearboxes, are bolted directly onto the engine block. Robotic torque arms perform these operations with absolute consistency, while sensors record every bolt's torque and angle to ensure mechanical integrity. Meanwhile, on the chassis line, rear axle assemblies are prepared in parallel. For models with multi-link rear suspension, this step includes fitting the control arms, coil springs or dampers, rear disc brakes, and sometimes independent electric motors for all-wheel drive variants. These modules are mounted onto jigs and temporarily stored until they're summoned into position by the main assembly control system, which tracks each vehicle's configuration in real time. Now comes the literal marriage of body and chassis, a highly choreographed operation involving synchronized lifts, conveyor positioning, and robotic alignments. The body of the Octavia, suspended overhead by a guided hoist system, is lowered onto the rolling chassis below with astonishing precision. This alignment must match dozens of mounting points simultaneously: engine mounts, subframe bolts, suspension towers, and driveshaft couplings. The hoist slows its descent incrementally, guided by both optical sensors and laser alignment systems. Once body and chassis are joined, a team of skilled technicians manually fastens the major anchor points, assisted by torque-limiting pneumatic tools. These connections are critical as they determine the vehicle's handling, NVH characteristics, and structural behavior under stress. Each bolt's completion is digitally recorded and verified in the manufacturing execution system, creating a digital fingerprint for the vehicle. Following this milestone, the car begins to resemble a finished vehicle. It now moves under its own chassis wheels onto the next phase: wheel mounting and fluid filling. Tires and wheels are mounted using automated stations that retrieve the correct size and style based on the car's build sheet. Steel wheels, alloys, summer or winter tires, depending on market and order. Robotic arms guide the wheels onto the hubs, while nut runners fasten them in a star pattern to ensure balanced torque distribution. With wheels fitted, the vehicle enters a sophisticated fluid station where all operating fluids are automatically filled. These include engine oil, brake fluid, coolant, transmission fluid, and refrigerant for the air conditioning system. Nozzles are inserted into designated ports, and the exact volume is dispensed under pressure control to ensure no air pockets or underfilling. The brake lines and fuel system are pressure tested during this stage for leaks, and any deviation triggers a diagnostic halt. Electrical systems are now connected and initialized. The vehicle receives its battery, alternator links, and fuse box connections. Diagnostic tools plug into the onboard OBD port to initialize and verify all electronic control units, engine ECU, body control module, infotainment systems, safety sensors, and more. This moment is often referred to as the car's first heartbeat, the first time it powers up electronically and is capable of communication and self-diagnosis. It's also now that the vehicle's doors, which were sent down a parallel sub-assembly line earlier, are reattached. During their absence, each door was fitted with inner paneling, window regulators, speakers, insulation, locking mechanisms, and trim. Robotic arms lift the doors back into position and attach them using high-torque fasteners. Workers verify door alignment, shut lines, and hinge tension to ensure smooth operation and flush fitting. Window calibration tools are also used to check automatic up-down functions, pinch protection, and sealing. At this point, the Octavia proceeds to the dynamic calibration area. Although the car is not yet ready for the open road, it undergoes an initial set of tests to calibrate sensors, align components, and validate subsystem communication. A wheel alignment station uses high-precision optical cameras to adjust toe, camber, and caster angles according to factory specs. Headlights are calibrated in beam testing bays, where optical targets are used to adjust the throw, height, and spread of the light, especially critical for models equipped with adaptive matrix LED systems. Next, the car undergoes brake and suspension testing on a rolling test rig. The vehicle is driven onto a large multi-roller dynamometer where the wheels spin under resistance. During this process, technicians activate the braking system, monitor deceleration curves, and verify that ABS and ESC systems respond as programmed. The suspension is also checked for compliance and noise using vertical shakers that simulate uneven road surfaces. Any creaking, excessive travel, or rattling results in an immediate pull for inspection. A particularly fascinating step follows: the water leak test chamber. Every single Octavia is driven into a sealed tunnel where high-pressure water jets blast the entire vehicle from multiple angles. The test simulates intense rain, car washes, and flood-like conditions. Sensors placed inside the cabin, along with absorbent test materials, detect even the slightest intrusion of moisture. This ensures the integrity of window seals, door gaskets, light assemblies, and sunroof drains. Emerging dry and intact from the water test, the Octavia proceeds to the finishing line, where final interior fittings and cosmetic elements are installed. This includes steering wheels, emblems, gear shift knobs, floor mats, decorative trims, and external badges. Infotainment software is uploaded or updated over a secure network, often using factory-wide Wi-Fi protocols. The vehicle's VIN is permanently etched into structural components and logged in the company's global tracking system. One of the last human-centric inspection areas is the quality audit tunnel. Here, specially trained inspectors perform a 360-degree check under high-intensity lighting to detect any aesthetic flaws, paint imperfections, trim misalignments, stitching errors, or even tiny scratches on window glass. They also run functional checks, including horn operation, screen responsiveness, ventilation airflow, mirror adjustability, and seat motor function. Every button, switch, and knob must perform flawlessly. Before the vehicle can be declared finished, it must complete one more critical phase, the road test loop. A selected percentage of vehicles from each production batch, typically 1 in every 20, are driven on a dedicated outdoor or indoor track. This track simulates real-world driving conditions: cobblestones, sharp turns, acceleration zones, and braking areas. Skilled test drivers listen for unusual sounds, assess steering response, and monitor transmission behavior. Advanced onboard diagnostics log performance metrics throughout the test drive. Once approved, the Octavia returns to the factory's logistics area, where it undergoes its final configuration. Region-specific features such as language settings, radio frequencies, emissions labeling, and immobilizer coding are finalized. Vehicles destined for specific markets, Germany, UK, Scandinavia, or overseas, are grouped together and scheduled for shipment. Once a Skoda Octavia rolls off the production line, fully assembled, tested, and approved, it doesn't simply sit idle awaiting its new owner. What follows is an equally critical, meticulously orchestrated process that transitions the finished vehicle from factory floor to dealership showroom. This final stretch of the production journey may not involve welding robots or paint curing ovens, but it requires an intricate ballet of logistics, digital systems, quality assurance, and environmental controls to ensure that each car arrives in pristine condition, configured perfectly for its destination market. The first step begins at the vehicle dispatch yard, a massive, secure expanse typically located adjacent to the main factory grounds. This area operates like an open-air inventory matrix. Rows of finished Octavias, arranged by drivetrain type, paint color, market region, and model variant, are lined up with absolute geometric precision. Each vehicle's location is tagged via RFID or barcode systems and updated in real time into Skoda's global logistics management platform. The platform tracks not only the physical location of each vehicle, but also its production status, destination, and shipping schedule. Before any vehicle can be released for shipment, it undergoes a final series of checks in the pre-delivery quality assurance zone. This area acts as a last filter to catch any deviations that might have occurred during the assembly or post-test handling stages. Workers inspect tire pressure, verify that protective films are applied correctly to scratch-prone areas like door edges, mirrors, and bumpers, and confirm that all software systems are up to date. Vehicles fitted with GPS or SIM-based connectivity receive final activation or regional adjustments depending on local telecom regulations and data privacy laws. Another important step here is the market-specific homologation procedure. While the Octavia platform is globally standardized, various regulatory requirements differ from country to country. Vehicles destined for the UK, for example, require right-hand drive steering, headlight angle adjustment, and specific compliance markings on safety stickers and child lock labels. Similarly, North African or Middle Eastern versions often come with enhanced cooling systems, battery conditioning for high temperature zones, and multilingual interfaces for infotainment and vehicle manuals. Each car is thus finalized for its end user region with absolute attention to detail. Once cleared for dispatch, the logistical journey begins. Cars are loaded either onto multi-deck car carrier trucks or specialized automotive freight trains, depending on destination. For continental European markets, rail transport is the norm, as it allows for the movement of dozens of vehicles at once with low emissions and high security. These trains are purpose-built with adjustable platforms to accommodate various vehicle heights and lengths, and the loading process itself is conducted using hydraulic ramps and wheel guides to prevent any possibility of contact or scratching. Vehicles are secured in place using soft straps over the tires, never hard points on the bodywork, to avoid any damage. Drivers and loaders follow strict speed limits and turning angles during the loading process, and each movement is logged electronically with timestamps and operator ID for full traceability. The outbound transport system functions on just-in-time scheduling. Transport is aligned tightly with dealership stocking cycles and customer orders, meaning that most Octavias are delivered to retail networks within days of completion. For overseas markets such as Australia, Japan, or South Africa, the vehicles are routed to maritime logistics hubs, most notably in German ports like Bremerhaven or Hamburg. Here, cars are parked in holding zones until their shipping vessel arrives. Before boarding the ships, known as roll-on, roll-off, or ro-ro vessels, each Octavia undergoes a salt spray protective procedure, which includes the application of temporary wax coatings on vulnerable areas like undercarriages and wheel wells. Mirrors are often folded in or protected with soft plastic covers, and battery terminals may be disconnected during long journeys to preserve charge levels. Ro-ro vessels are essentially floating parking garages. Cars are driven into the lower decks via wide ramps, then secured in rows using floor hooks and wheel chocks. Temperature and humidity are monitored throughout the voyage, and any incident or deviation is logged and communicated back to Škoda's central logistics team. These teams use real-time satellite tracking and predictive ETA algorithms to coordinate arrival times, customs clearance, and inland transport schedules for each destination port. Upon arrival in the destination country, the vehicles are offloaded and temporarily stored at an importer's distribution center, known in industry terms as a vehicle processing center. These centers act as a final staging ground before cars are delivered to dealerships. Here, the Octavia undergoes another series of inspections and market preparations. Protective films are removed, final cleaning is done, and country-specific accessories like license plate frames, floor mats, or regional documentation packets are added. The vehicle's onboard software may receive updates or localizations, such as voice command packs in specific dialects or region-locked infotainment functions like radio bands or mapping data. Any vehicle requiring customization at the VPC, such as fleet vehicles with special paint schemes, decals, or upfitting, undergoes a rapid accessory installation. This is also the point where final compliance documents are printed and affixed, including emission certification, tire labeling, and VIN stickers that align with the country's Department of Transportation or equivalent authority. Once cleared, the car is loaded onto local transport carriers, usually single or double-deck trucks designed for short-haul deliveries to regional dealers. These trucks operate on a tightly managed schedule coordinated between the manufacturer, logistics provider, and the dealership's sales team. Dealerships receive advance notice of incoming units, complete with full configuration specs, production history, and electronic handover documentation. This allows showroom staff to prepare for vehicle delivery, organize customer paperwork, and schedule test drives or handovers for buyers who've pre-ordered their Octavia. Upon arrival at the dealership, the vehicle enters the final stretch of its preparation life cycle. Dealership technicians perform what's known as the pre-delivery inspection. This process involves checking battery voltage, verifying tire pressures again, updating software to the latest firmware release, and confirming that all onboard systems are functioning correctly. The technician also syncs the vehicle's telematics systems with the customer's profile if it's a connected vehicle, ensuring seamless onboarding for the driver. Exterior cleanliness and presentation are paramount here. The vehicle is washed, dried, and polished. Any interior protection, seat covers, plastic film on displays, is removed carefully to preserve the new car sensation. The vehicle's infotainment system is often demoed for the customer in advance, showing off features like wireless Apple CarPlay or Android Auto, adaptive cruise control settings, or integrated Škoda Connect services. The car is now ready for customer delivery. But beyond just logistics, the entire system that supports the delivery of the Škoda Octavia is also an achievement in manufacturing scalability and digital synchronization. Every car, from the moment a production slot is assigned to the instant its keys are handed over to a new owner, is tracked, scheduled, configured, and quality controlled to within an inch of perfection. Even after the sale, onboard diagnostic tools and telematics systems report service needs, software, update availability, and potential issues, creating a lifecycle loop that feeds directly back to Škoda's engineering and production planning teams. For example, if a particular batch of Octavias reports slightly increased wear in rear suspension bushings under certain climate conditions, engineers can trace the data back to specific suppliers, production dates, and even sub-batch quality readings. This creates a feedback loop that not only improves future vehicles, but enhances predictive maintenance and customer satisfaction. Behind the gleaming bodywork, smooth ride, and modern technology of each Škoda Octavia lies a staggering network of systems, people, machinery, and logistical engineering. From zinc-coated steel coils and precision robotic welds to cross-continental transport vessels and digital dealership diagnostics, the Octavia isn't just built, it's orchestrated in harmony with thousands of moving parts and processes, each time to perfection. And all of it, every robot weld, every bolt tightened to exact Newton meters, every barcode scanned, is done not simply to build a car, but to deliver an experience, one of reliability, safety, performance, and pride of ownership. That's the promise that begins in the factory and ends in the driver's seat. To truly understand the scale and precision behind Škoda Octavia production, one must look beyond the factory floor and consider the intricate network of component suppliers and upstream systems that feed into the assembly line. For every car that takes shape in the factory, hundreds of specialized parts must arrive on time, in the right sequence, and in the correct specification. This vast, synchronized network is known in the automotive world as the supply chain, and in the case of Škoda, it's a marvel of real-time coordination, supplier partnerships, and just-in-time logistics. Each Škoda Octavia comprises over 6,000 individual parts. These components range from large visible systems like wheels, windshields, and headlights to invisible but critical parts like engine sensors, fuel injection regulators, gasket seals, and control module chips. Roughly 65 to 70% of these parts are manufactured by Tier 1 suppliers, companies that deliver fully assembled modules or high-value systems directly to the carmaker. The remaining proportion includes Tier 2 and Tier 3 suppliers that deliver subcomponents to the Tier 1s for further integration. Consider the dashboard module, for example. This is not simply a plastic structure. It includes integrated climate ducts, wiring harness brackets, infotainment mounts, and sometimes even embedded ambient lighting strips. A supplier like Faurecia or Lear might produce this complete dashboard unit off-site at a satellite plant located within 50 to 100 kilometers of the main Škoda facility. Their production runs in parallel with Škoda's own line, synchronized by shared production schedules and EDI systems. These EDI platforms are the backbone of modern automotive manufacturing. Through these systems, Škoda communicates real-time build orders to each supplier based on customer demand, line performance, and inventory levels. If a sudden influx of Octavia orders requires an uptick in 1.5 TSI engines with manual gearboxes, Škoda's system sends this data down the chain, prompting engine module suppliers to adjust output and delivery timing. This just-in-time model reduces storage needs and waste, but it requires near-perfect execution and reliability across the board. Every part entering the Škoda plant is tagged with unique barcodes or RFID labels. Upon arrival at the factory gates, incoming deliveries are scanned, inspected, and logged. The parts are then sent either directly to the line or stored in high-efficiency automated warehouses called ASRS. These towering computer-controlled storage units use robotic cranes and conveyors to quickly retrieve parts as needed, feeding them into the production line in a seamless, real-time flow. But the supply chain is about more than just timing. Quality control is paramount. Each supplier is required to adhere to Škoda's supplier quality standards, which are monitored through periodic audits, statistical process control data, and end-of-line checks. If a batch of components falls outside tolerance, say windshield washer motors with torque output below spec, they are quarantined and the supplier is notified immediately via automated quality feedback portals. This attention to quality also extends to the software components in modern Octavias. Today's cars are as much digital machines as they are mechanical ones. Software for ECU modules, infotainment units, ADAS, and telematics is developed months in advance and tested in closed-loop systems before being validated for installation. These software packages are pushed to the factory through secure networks and flashed onto control modules during vehicle assembly. Security is paramount here, and all software updates are cryptographically signed to prevent tampering or breaches. Now, let's turn to automation, one of the defining features of modern Škoda production. While humans remain central to the assembly process, particularly in tasks requiring judgment, dexterity, and customization, the factory itself is driven by an intricate web of automated systems. Conveyors, robots, AGVs, and digital twins all work in harmony to keep the line moving with minimal interruption. AGVs are one of the most visually striking elements of this system. These robotic delivery vehicles navigate factory floors autonomously, delivering everything from suspension arms to steering wheels to the correct workstation, guided by a combination of magnetic tracks and onboard LiDAR systems. Each AGV is linked to the MES and can reroute itself based on real-time production changes. For example, if a specific model is delayed in paint, the AGV carrying its corresponding seat set can be redirected to a holding buffer without human intervention. Overhead, conveyor systems run in tandem with the floor-level automation. These ceiling-mounted rail systems transport car bodies from one section of the plant to another, lifting and rotating them to allow ergonomic access for workers and robots. In some areas, these conveyors also include turntables and elevator modules that adjust height and orientation based on the assembly phase. This ensures not only productivity, but also worker safety and comfort. One of the most powerful tools in Škoda's production arsenal is its use of digital twin technology. Every car moving down the line has a virtual counterpart in the cloud, an exact digital representation of its configuration, assembly status, component origins, and inspection results. This digital twin is updated in real time and can be accessed by plant managers, quality engineers, and logistics coordinators. If an issue arises, say a misalignment detected in a body panel, the digital twin records the anomaly, associates it with the production station and shift in which it occurred, and notifies the relevant teams for root cause analysis. Digital twins are also critical in training and simulations. Before a new variant of the Octavia is introduced, engineers and planners can simulate the entire build process, testing new tools, layouts, or work sequences in virtual space. This allows Škoda to implement changes quickly, with minimal disruption to ongoing production. It also reduces the number of physical prototypes needed for process validation, saving both time and cost. While robotics handle many of the repetitive and high-precision tasks, human workers remain essential, particularly in the trim and final zones, where interiors, wiring, and complex assemblies come together. To assist them, Škoda deploys a suite of ergonomic tools and digital aids. Torque-controlled power tools connected to overhead reels allow workers to fasten components without strain. Visual instructions and torque values are displayed on smart monitors at each station, updating in real time based on the vehicle moving down the line. Smart gloves and wearable scanners are also used, allowing technicians to confirm part identity and orientation before installation. Each human operator is trained extensively, with many going through weeks of classroom instruction, simulator-based practice, and shadowing experienced colleagues. Certification is required for each workstation, and retraining is done periodically or whenever a new process is introduced. Safety is integral to all of this. Sensors monitor motion zones to prevent collisions. Alarms trigger if tools deviate from preset thresholds, and workspaces are equipped with height-adjustable platforms and cushioned mats to reduce fatigue. Behind all of this is a powerful production planning system. Long before a single Octavia reaches the line, planners model capacity forecasts, supplier lead times, labor scheduling, and shift rotation schemes using AI-based algorithms. These tools factor in order backlogs, regional model demand, holidays, and even weather patterns that might affect logistics. If a snowstorm is predicted in a key transport corridor, the system automatically recommends schedule shifts or alternate distribution routes to avoid disruption. Energy efficiency is another area where Škoda has made major strides. The factory is equipped with heat recovery systems, solar arrays on the roof, rainwater harvesting systems, and intelligent lighting that adjusts based on occupancy and daylight levels. Paint shops, traditionally among the highest energy consumers in automotive production, are now equipped with dry scrubber technology and thermal recirculation to minimize waste. Even conveyor motors are equipped with regenerative braking systems to recover energy during deceleration phases. Sustainability doesn't stop at the factory gates. Suppliers are audited not just for quality and delivery performance, but also for environmental and social responsibility. Škoda enforces compliance with ISO 14001 standards across its tiered supply network and encourages local sourcing where feasible. Packaging materials are standardized and reusable, and component shipments are consolidated wherever possible to reduce carbon footprint. To further appreciate the engineering and manufacturing depth of the Škoda Octavia, one must explore the extensive customization capabilities and flexible production architecture that allows this single vehicle line to cater to a wide global audience. The Octavia is not a one-size-fits-all car. It is offered in multiple body styles, powertrain options, interior trims, and equipment levels, all of which are supported by a sophisticated manufacturing system built upon modularity, scalability, and lean manufacturing principles. At the heart of Škoda's flexibility lies the Volkswagen Group's Modulare Querbaukasten, or MQB platform. Introduced to harmonize development across different vehicle classes, MQB is a transverse modular toolkit that allows shared use of components such as engines, transmissions, suspension geometry, and electrical architectures across various models. In the case of the Octavia, it shares its underlying platform with vehicles like the Volkswagen Golf, Seat Leon, and Audi A3. This commonality enables Škoda to produce multiple variants of the Octavia: sedan, wagon, hybrid, gas-powered, diesel, and even mild hybrid versions, without requiring completely separate production lines. Rather than viewing the Octavia as a single product, Škoda treats it as a configurable structure within a tightly coordinated production matrix. When a customer places an order, either through a dealership or an online configurator, that order flows into Škoda's central planning database, where it's translated into a digital build sheet. This document specifies every aspect of the vehicle: engine type, transmission, drive layout, infotainment system, upholstery, wheel design, active safety packages, regional adaptations, emission certifications, and even factory-installed accessories like roof bars or tow hitches. Each of these variables is governed by a set of compatibility rules managed by Škoda's product configuration logic. For example, a high-output diesel engine may not be available with the base trim level due to cooling and chassis constraints. Similarly, specific radar-based safety systems might only be installable on variants with a certain type of front bumper or interior digital cockpit. These conditional dependencies are resolved automatically by the back-end systems, which check for engineering feasibility before locking in the order. Once an order is confirmed, it is slotted into a dynamic production schedule that balances model mix, resource availability, and factory efficiency. Importantly, Škoda does not build vehicles in strict order of sales. Rather, it builds them in an optimized sequence that minimizes setup time, balances labor load, and stabilizes part consumption rates. This method, sometimes referred to as level scheduling, is one of the cornerstones of lean manufacturing. It prevents bottlenecks, allows for better supplier coordination, and reduces the amount of time the car spends in the factory. As a result, two cars traveling down the line might look identical from the outside, but be completely different beneath the surface. One a plug-in hybrid with heated rear seats and check navigation, the other a base model petrol version for export to North Africa. To manage this complexity, each station along the line reads the vehicle's digital build sheet in real time. Screens above the workstations display step-by-step instructions tailored to that exact configuration, while pick-by-light systems guide workers to the correct bins and component trays. This is particularly important during interior assembly, where the number of possible permutations is vast. From dashboard colors and decorative inserts to seat foam densities and steering wheel types, the interior is one of the most customized parts of the car. Workers receive seating units pre-tagged with RFID matched to the car via an automated delivery system. The steering column, infotainment interface, gear selector, and even pedal assemblies are chosen based on each vehicle's order code. Robotic torque arms are reprogrammed automatically to apply different fastening sequences depending on the equipment level and trim variant. The same modular logic applies to the powertrain station. The MQB platform allows various engine and transmission combinations to be mounted onto the same chassis architecture. Whether a car is receiving a 1.0 TSI petrol engine or a 2.0 TDI diesel with all-wheel drive and DSG transmission, the mounting points, wiring harness routing, and cooling integration follow standardized paths. The robotic systems that perform engine marriage operations adjust in real time based on the digital instruction set received for each car. Emissions compliance is another area where the system's flexibility shines. Vehicles bound for different regions must meet different regulatory standards: Euro 6D in Europe, Bharat, Stage 6 in India, or Tier 3 in the United States. This affects more than just engine calibration. It can influence the selection of catalytic converters, onboard diagnostics, fuel vapor recovery systems, and exhaust layout. The assembly line is capable of dynamically adapting these configurations during the final powertrain integration phase. Emission sensors are tested and validated before the car moves to final quality check, ensuring full compliance before leaving the plant. This high degree of customization has forced Škoda to develop exceptionally refined in-house logistics and traceability tools. Every part, from a bolt in the seat frame to the circuit board inside a camera module, is traceable back to its source, down to the supplier batch and timestamp. If a defect is later discovered in a specific part, such as a faulty capacitor in an ABS module, Škoda's quality team can instantly identify all affected vehicles, notify dealers, and even pre-position replacement parts for proactive service campaigns. But the complexity doesn't end at physical hardware. Modern Octavias are packed with software-controlled systems: lane assist, adaptive cruise control, parking sensors, matrix LED lighting, automatic emergency braking, and connected infotainment platforms. Each of these systems has embedded firmware that must be updated and calibrated before delivery. In some cases, over-the-air updates can be performed after the car is sold, but many functions still require factory-level activation and testing. To streamline this, Škoda uses central configuration tools that compile a software bill of materials for each vehicle. As the car moves through assembly, each electronic control unit is flashed with its specific firmware version, encrypted and authenticated via secure keys. A final system integration test validates that all ECUs are communicating properly, known as a KN bus verification, and that diagnostics are error-free. If any faults are detected, the car is automatically diverted to a diagnostics bay for further analysis. Such granularity and flexibility would not be possible without an empowered and highly skilled workforce. Škoda invests heavily in training and upskilling its production teams. Every new employee undergoes a rigorous onboarding program that includes mechanical skills, safety procedures, quality assurance basics, and an introduction to the Škoda production system. For specialized roles like engine mounting, suspension calibration, or electrical integration, additional certifications are required. These are renewed annually to ensure procedural consistency and up-to-date knowledge. Continuous improvement, or Kaizen, is another foundational principle. Employees are encouraged to identify inefficiencies or risks and propose improvements through structured feedback channels. Many line-side innovations, such as tool redesigns, ergonomic adjustments, or improved material handling flows, originate from shop floor operators. Each suggestion is reviewed by a dedicated process engineering team and, if feasible, rapidly prototyped and implemented. Even the work environment itself is engineered for performance and health. Škoda's factories are designed with natural light corridors, clean air circulation systems, sound dampening materials, and climate-controlled zones. Workstations are height adjustable, parts bins are positioned within optimal reach distances, and ambient noise levels are monitored to prevent long-term exposure risks. In areas with repetitive motion, exoskeletons or assistive lifting arms are provided to reduce physical strain. Škoda's ability to build thousands of highly individualized vehicles per week is not simply a triumph of machinery. It's a reflection of disciplined process design, human system integration, and scalable modularity. Whether assembling a performance-oriented Octavia RS with sport suspension and dual exhaust, or a fuel-sipping mild hybrid for city commuting, the line adapts fluidly. Every Octavia is not just a copy of the last. It is a response to a unique customer need, tailored precisely and efficiently thanks to the architecture of customization that Škoda has refined over decades.